Hello, this is Concrete Path, and today's lecture is about the columns. So columns those are compression members. Usually we say they are compression members. Compression members. Now let's say you have this you have this bar, you have this column. Let's take this as a column. You apply load of P, and the load is, and we say load is parallel to long axis. Load is in the direction of long axis. P is parallel to long axis, and the deflection that is the created deflection is perpendicular to the direction of load. Delta is perpendicular to the direction of load. And this phenomenon we call it as a buckling of that column. Buckling of that column. So when we studied that beam, we said there is long axis that was in the direction of x. We call that as x, and here the long axis is in the direction of y. So we say you apply load in y direction, and deflection was also in the y direction. Deflection was also in the direction of y. So I would say py parallel to delta y. So this is called as bending. So in the bending there is deflection in the direction of load. Deflection in the direction of load. So that was your bending. And for these columns we have the deflection that is perpendicular to direction of load, that we call as buckling. So let's say that you apply load, and deflection is perpendicular to direction of load. So you are applying load in this fashion. Let's say this is your column. You apply load in this direction, and it gets deflected by this laterally, that we have delta, and finally it reaches to some next location that we have at a distance of delta perpendicular to direction of load. So that we call it as a buckling of column. Now if we say that the load is purely along the axial line, so there might be some cross section. If the load is purely along the axis, we can call it as the stresses developed would be only axial. That would be P by A cross section. So that the variation would be along the entire we have what we call as along the entire cross section. The stresses would be compressive, and that would be P by A. So each fiber would have a stress of P by A, that is P by A stress. Now but this is not possible every time. When you design a column, there might be some eccentricity of that load. Let's say this is your that centroid, and load is not purely on the centroid. Load is at somewhere on one of the quadrants. I would say load is at some eccentricity. So because of that, there would be development of moments about these two axes. There would development of the moment about these two axes. So I would say there would be two stresses developed. One is your axial. When you transfer that into the centroid, I would say one is your axial stress, and next one is your bending stress. Because of moments. There would be PE by Z, or PE y by I, my by I. So these two things we have to keep in mind. Now one thing is that let's say that you have this column, and you apply a load of P. And it deflects, or we can say it buckles such that it reaches to some value of delta. Finally it is here. Now it's not. Now one thing is that, so you apply the load. Now you do one thing. You remove the load, or unloading. You unload that. After unloading, the material or the column comes back to its original position. Column comes back to original position. So that part, if the load is such that if the load is such that you applied it, there is some deflection delta, and you remove the load now. You remove the load now, and the column comes back to its original position. We say that this configuration, we call it as a stable configuration. Stable configuration. Now, one thing is that you applied a load of P1. You applied a load of P1, and it deflects by amount of, it deflects by delta. Now the thing is that it comes back in the first case. Now in the second case, it would remain neutral. That means it won't come back to the original position, so it remains here only. Now here it would remain fixed now. So this delta is remains constant now. It's not changing now after unloading. After unloading, there is no change in delta. The third one is that you applied, so this load we call it as P1. This was greater than P, initial load P. So this load was greater than P, and this we call as critical load, PCR. So critical load is there, on which there is a neutral equilibrium, I would say. And third one is that you apply a load of P2. Let's say you applied a load of P2, and it reaches to some delta 1 after time T1, and after time T2 it reaches to delta 2 in time T2, and delta 3 in time T3, and so on and so on. So it's unstable. We say this is unstable because your load 2 is greater than PCR. So it's unstable equilibrium. And this is a failure. We say this is a failure. This is a failure that's not material failure. It's not material failure. It's not material failure, but what it is, it's not material failure. But what is it is? It's an engineering failure. It's an engineering failure. Or we can say it's a member failure. Member is failing, not the material in the member. There is a material whose strength is more than so your strength for the material is more. It can take more loads. It can take more load as compared to P2, but the member itself is failing. It is not able to retain its position because of that load P2. So member is failing, member failure or engineering failure. So your material can take strength more. Material can take load more than that P2. But your overall member is failing. It's failing because there's some engineering failure. We say there is some engineering drawback of that design. So there we have these three kinds of equilibrium. So let's talk about that. See, this load, even this load P2 by area cross section, there was some stress. It was even lesser than yield stress. It was lesser than even yield stress. Even lesser than yield stress, but still it has failed not because of material failure, but because of member failure. So let's have that. So based on this, we say that there might be three kinds of columns. We have three kinds of columns. So one is that we call a short column. Next one is that a long column, and third one is that a intermediate column. That short column we say that means length is less, and it fails by material failure. So there is material failure. So material is failing means stress is greater than sigma yield of that material. And in the long column we say length is very much, and there is member failure, not material failure. Member failure. That means stresses are even lesser than yield stress, but material is failing, but member is failing. And third one is that it has the characteristics of both. So we say both failures happen, both crushing and yielding. We say both crushing and buckling of material. So we have that theory. We have that theory of buckling. We call it as Euler's theory of buckling. That's Euler's theory of buckling. Let's write that for the columns. We have Euler's theory of buckling, and it's for long columns. Long columns means they undergo buckling. So by the material, by the Member failure, we say this member goes under buckling mode. That means it deflects by some delta, and because of that instability, it's not able to retain its position, so it's unable to take more amount of loads, even that's even causing stresses lesser than the yield stresses. So we will be talking about long columns and in the case of buckling. So let's have that Euler's theory of buckling for the long columns. So we say you applied a load, and we say that your supports are hinged supports. We say supports are hinged. Both ends are hinged. Or we say pinned. Now we apply load of P. What's happening that we say the configuration now looks like in this fashion. So apply a load of P, and because there is pins at the ends, because there are pins at the ends, it can't go anywhere. There won't be delta on those ends. So but there would be some delta formed at the mid somewhere. So we say there is some delta formed in this fashion. So we say that this is some buckling has developed, and we say delta here is 0, and similarly delta here is also 0. And we say that you go to some value of x, and we say there we go to some value of x, and we go to some value of, there we have some value of y buckling. Y amount of buckling is there. So buckling is y at that x from one of the sides. Now if we take that section, so we say there is some load of P, and there is some shear force, and there is some bending moment mx on that section. Now if you want to balance that, if you want to apply summation of moments on that section equals to 0, I would say P into some value of, this was your y value, so P into y, that's anti-clockwise, and minus mx anti-clockwise, that is 0. So some moment, bending moment at x equals to minus py. And if I write that equation of equation, we have that general equation that ei d2y by dx2 equals to m by m, or we have that this is in this fashion. Do you know this equation? That curvature of the beam is m by ei. So if I use that equation, this equation now, so mx I can write mx by ei. So similarly I would write minus py by ei. So if I use this equation, because there is some delta, so I want to say what is this delta in terms of that load. What's this delta format? So I would say d2y by dx2 and plus py by ei, that is equals to 0. Now the thing is that if I keep it in terms of this one, d2 y by dx2 plus some m square y by ei, m square is equals to m square y equals to 0. So where your m square, I have kept it as equals to p by ei. So if we have this equation. Now applying that operator, I would say d square plus m square of y equals to 0. So I have the general solution of this differential equation. Solution of this differential equation gives you y equals to a sine mx plus b cos mx. So so finally we got this equation of deflection at any location. So I can get the delta at any location. So I got the delta at any location, that at any location of x, what is the delta that has developed. Now if I apply boundary conditions that at x equals to 0, the delta is 0, and at x equals to length of L, your delta is also 0. So if I apply boundary conditions that at x equals to 0, delta is 0. So if I use this condition, I would say 0, or delta in terms of, we can write y equals to 0. So 0 equals to a 0 plus b into 1. So b equals to 0. And similarly, x equals to L, y equals to 0. 0 equals a sine ml plus 0. It's already 0. So I would say that a can't be 0. Why? If a is 0, so your equation would become y equals to 0 plus 0. So that means deflection is 0 at every point. Deflection is 0 at every point. Every point we have, every point at every x we have delta as 0. That's not possible. We say that you apply load, there is some delta developed, you apply load of P on this column, and it's sure going to have some deflection delta. So delta cannot be 0. So we say that delta a won't be 0 such that I would say sine ml can be 0. So there is possibility that sine ml is 0. So if the sine ml is 0, on what values of that pi we have that sine function 0. I would say that ml equals to n pi. ml equals to n pi. Okay, some integral values of pi. On that your sine function equals to 0. So such that if I square this, I would say m square l square equals to n square pi square. And if I use that value of m square, I know the value of m square equals to p by ei. So I write that p by ei, l square equals to n square pi square. Now if I write that p equals to n square pi square ei by l square, so I got this equation that how much load it would take to create that buckling critical load. What is the critical load on which that buckling is possible, that neutral equilibrium is possible, such that it would remain at that position. Now you applied that load equals to PCR, such that it is in neutral equilibrium now, such that it's if the load is now, if the load you applied P1 such that it is greater than PCR, so there would be instability. So unstable equilibrium would get developed. So this is the critical load on which that neutral equilibrium is getting developed. So let's apply that values of n. So let's apply n equals to 1. We would see what is this value giving me. So that value equals to pi square ei upon l square. So this pi square ei upon l square. So that means if the length between the two those ends was equals to l, and the ends were pinned, or we can say hinged, the ends were hinged, we say this condition we can call it as single bow condition. That at n equals to 1, your value of p is equals to pi square ei upon l square. So that means there is some deflection, and there is only one bow that has developed. Only one bow, we'll call it as bow. So one bow has developed. So that's why we call it as a single bow condition. And this value of load that we call it as a PCR, that is critical load of that buckling, critical buckling load. Let's call it as a Euler's critical buckling load. Euler's critical buckling load. And if you take n equals to 2, we can get that PCR equals to pi square ei and 4 times by l square. So we get that at n equals to 2, your load is 4 times, becomes your critical load, that is that column can take, that is 4 times initial load. So there, by changing that condition of n, your column can take now more amount of load, that's 4 times. So that means if there are 2 bows formed, the member can take 4 times the load, initial load, to get that buckling that character or neutral equilibrium condition. So we say that for this condition n equals to 2, we say this is double bow condition. So what's happening actually? Actually the total length was L, and now the length has reduced to L by 2. So if I write that L by 2, that total L in terms of L by 2, so if I write this equation that PCR equals to pi square ei by L by 4, and I would write in terms of this L by 2 whole square, such that it becomes L square by 4. So if I write this equation in terms of this one, that L actually here is L by 2. So what's happening, that by changing that length, we call it as an effective length, by changing the effective length between the two spans, your load critical load also changes. It varies with that length of L. We can call it as effective length. So your effective length now here we can say L by 2. Here the length is also L by 2. Because that effective length decreases, here your critical load increases. There is an inverse relation. We say. So similarly, if you use n equals to 3, we have 9 times that critical load. PCR equals to that 9 times. So that means there is some connection between that critical load and what we call as length, and this we call as effective length. Let's call it as effective length, LE. So what's actually LE? So let's study that. What's LE? So you take so few examples of that. You have that simply support beam. You apply load of UDL that, and we say what is the bending moment diagram looks like. How is the bending moment diagram looks like? We say we have that maximum WL square by 8, and at the end spans we have bending moment of m equals to 0, So we said that the total length is L. There is bending moment at the ends equals to 0. And similarly, there is one more thing. You take that cantilever beam, apply load, and we say what is the bending moment diagram? How it looks like? So we say there is some variation in this fashion. So we say that there is bending moment somewhere here, that is 0, and there is some bending moment here, that is 0. That's point of contraflexure. So we say that there is some length where the bending moment is 0 between the two those edges. There are two adjacent points where the bending moment is 0. So we call it as effective length. That we have. Similarly here, we say that the distance between two adjacent points. So let's try what effective length means. That distance between two consecutive points of zero moments. So that we have effective length. So for this case, we say that effective length equals to L, and for this case, there is some less length. So there is some length of A, there is some length of also A. We said there is some length L minus 2A. So effective length is L minus 2A. And you take that example of propped cantilever. You apply the load, and I would say, what is the BMD? How does the bending moment diagram looks like? We say there is some bending moment diagram in this fashion. So there's some point of zero moment. And that length we have LE, and that's some length of x. That's some length of L minus x. So I would say we got these different conditions. Let's take that now. The condition of that cantilever beam. You apply load of P, and what is the bending moment diagram looks like? So it looks like this one, PL. So there's only one point here. We say that bending moment is 0. Now if we say there might be one more imaginary length of L, such that if it is symmetric about that that fixed side, I would say there is one more bending moment diagram from the other side, such that here is also one bending moment that is 0, 0, 0. So I would say so effective length we would take as 2is L. So we have these different conditions, and for the first condition we have that Euler's buckling was Euler's critical buckling theory that was proved for. That was the condition for both ends are hinged. And we saw that if there is simply support beam with simple support, that is both ends are hinged or pinned, and for that effective length was equals to L, because your bending moment diagram is showing that moment is 0 at the ends. And similarly here we saw that delta is 0 at the ends. And because of that we got this equation that PCR equals to pi square EI upon L square. For value of n equals to 1, we got that PCR equals pi square EI upon L square. Now we take now different conditions that if the value of R is changing, if the value of that those we call it as ends, if the end condition is varying, that is your effective length is also varying. So let's take the second case that we will take that one end we can take as hinged or pinned. One end is hinged or pinned, and next one we can take next is fixed. next is fixed. So this is second case, that this is the second case. Let's take that second case. I would say one end of the column is fixed, and second end of that column is hinged. So there's some hinge support here. Now you apply load of P. Now you apply a load of P. I would say you apply some shear force of V also. You apply some shear force of V also. Now I would say there would be some shear force developed here also. There would be some reaction developed here also, and there would be some moment also developed M on this side. So I would say that the deflection profile would be in this fashion. Deflection profile here, the moment here, the delta theta would be 0, delta would be 0. So and that hogging curvature would be some sort of hogging curvature. Then in this fashion the deflection would be, I would say, buckling would be in this fashion. Here the theta is some value of theta, and I would say you are applying a load of P here. You are applying a shear of V here, shear of V here, and you want to say at a particular location, that at some value of x, what is the delta equation for that? What is the y value here? So if I cut that section, I would say you are applying a load of P here, you are applying a shear of V here, and you are at a distance of x, and the delta here developed is equals to y, and there is some moment of mx here developed, and there's some shear force. There's some shear force. We don't care about the shear force. We are worried about that bending moment, which is causing that deflection. So I would say let's apply that summation of moments at that section. Summation of moments at that section equals to 0. So that means your P into y anticlockwise, and minus times Vx anticlockwise. And one more thing is that we can call it as mx, that's also anticlockwise, that is equals to 0. So mx equals to minus py minus vx. So if I write that equation of bending, we say d2y by dx2 equals to minus py minus vx. So if I write this EI divide, if I divide it, I would say we got this equation. Now we keep the equation in terms of that function of y. So let's give that that differential equation in terms of y equation. I would say that d2y by dx2 plus by by ei and equals to minus times v by ei of x. So let's write that. I would say let's have some assumption. Let's take some values that m square equals to p by ei, and your s square equals to minus v by ei. So let's try that. So we would get that equation of d square plus m square of y equals to some value of s square x. So I would say that the solution of this differential equation would yield some value of the differential solution is equals to y equals to a sine mx plus b cos mx plus some value of s square by m square into x. So let's write that boundary conditions now. If I apply the boundary conditions, I would say at y equals to 0, your delta is 0, your y is 0. Yeah, at x equals to 0, your delta is 0, y is 0. So that means 0 equals to 0 plus b plus 0. So that means p is 0. And if I apply that next condition, that at x equals to L, your y is also 0 because we have fixed end. So at x equals to 0, your delta is 0. And at x equals to L, we have delta also 0. So if I use that equation now, I would say your delta is 0 at a sine ml, sine of ml, and plus some value of this one is already 0. This one is already 0 now, and we are left with that s square by m square into L. So we got this equation. Now the thing is that if I substitute the values of s square and m square, let's have that we would see what is the value we are getting. So value of s square by m square, that's p by ei minus v by ei. So that's v by ei divided p by ei into some value of L is plus a sine ml. A sine ml equals to 0. So we got some value of that a sine ml a sine of ml equals to v by p of L. So we got this equation. But we don't know the value of A. We don't know the value of A. We don't know this value of we don't know the value of sine function ml. So we say that one more thing we can do. We can have that. We have one more condition that theta is 0 here. We know that theta is 0 at x equals to L. We know that theta equals to 0, and theta is that dy by dx equals to theta. Dy by dx equals to theta. If I use that equation also, once we got the equation of y, if I write what is the dy by dx, that is theta, and that we have equation of a sine integral, that's a sine of differentiation of sine function, that is cos function, that's cos mx into some value of m. So we got this equation, and when we have this one also, differentiation of this one would yield that s square by m square plus s square by m square. So we got that theta equals to am cos mx plus s square by m square. And if I apply the boundary condition that at x equals to L, theta is 0. So I would say your 0 equals to am and cos of m into L, plus s square by m square. So I got the equation that let's take this equation as equation of that. I would write in terms of am cos of ml is equals to minus times s square by m square, and I know the value of s square by m square. I would say that is minus times v by p. That's v by p. So I got two equations in terms of sine and cos, and we have that v by p also. So if I have these two equations, so if I say a sine ml by am cos of ml, that is equals to v by p of this is top, L is at the top, so vl by p, and from this side we have this one. Actually the s square by m square is minus times of v by p, minus times of v by p, and we write that. So finally you got this one, vl by p, and from the bottom I would write plus v by p. So I got this equation now. Finally I would say we got some function of tan. So I would write 1 by m and tan of ml is equals to some value of that is L. That's L. So finally I write tan of ml equals to ml. So I got this equation now, final equation. So we have this equation that tan of some function is equals to that ml, tan of theta equals to, let's say, theta. So for this case we say there's some that smallest root of this equation would yield that smallest root of that equation is equals to that is 4.4934. Smallest root of this equation is equals to 4.4934. And if I use that value of m, we know the value of m is equals to m square equals to p by ei. So smallest root of that ml equals to 4.4934. So if I use that equation of that, if I square it now, let's have that square in this next step. I would say m square L square is equals to 4.4934 square. Now I write the equation of p by ei. L square equals to some value of 4.4934, and that value is equals to some value of 2.0. Let's write that 20.1906. Now I would say I want this equation in terms of that Euler's equation, p is equals to pi square ei upon L square. Some value of pi square ei upon L square. How can I make this? So if we kind of make it in terms of that pi square, so I would say let's convert it this part in terms of pi square. So finally we get some value of P by EI. L square equals to 2.044 pi square, and we approximate at this value equals to 2 pi square. So finally we got the equation that PCR equals to, let's keep it a P. So we got that equation of P equals to 2 pi square EI upon L square. But the equation of that Euler's critical load was equals to pi square EI upon L square. So if I want to keep it in terms of that effective length, then I have to convert this length in terms of effective length. So if I use this part in terms of effective length, let's say I'm going to take it in terms of that, I would write then P square equals to pi square EI by L by root 2 square. So such that your, I would say, effective length is equals to L by root 2. So that's general equation. We say the general equation of that Euler's critical load, that is in terms of L effective. That is in terms of L effective. So that's why your condition of that L effective is changing. So for this case, we say that effective length should be L by 2, such that overall value. So overall value is equals to, in terms of that, pi square EI by L effective square. This is your critical load. So this is the general equation, and from that we are changing that effective length, and your critical load is also varying. So for this condition, we say effective length is L by root 2. So similar to that of proper cantilever, that we apply load, and there is some BMD that has developed. So we say bending moment is 0 at the 2 points, and we can say similarly in this fashion. I would say you had that one end is hinged, next one is fixed. So you apply load P, then what's happening? Your deflection is developed in this fashion. We say there's some bending moment here, that's point of inflection or point of quadriflexion, you can say, and there's some bending moment 0 here. So this length of L effective equals to L by root 2, 0.7 approximately, 0.7 L. Now we have the third condition that if the both ends are fixed, if both ends are fixed, let's have that condition. So we say that you apply load of P, and based on the symmetry, if the load is such that, let's say load is at the midspan, we say shear force is 0 at the midspan. This one, not shear force is 0. We say now you apply load here. In this case we are talking about. So you apply load. Let's say there's some load, and there's some load, and there might be some shear force, and there might be some shear force P, V, P, and there is some moment developed M. There is also some moment of M. Let's say there's some moment of M. Developed. So we say there's a possibility that deflection would be somewhere maximum at the midspan, and because ends are fixed, there won't be delta and theta at the ends, and there's a possibility that delta would be maximum at the end, that midspan. So if I have that, I would say at the ends there would be some hogging curvature, and after that there is some sagging. Similarly here also, I would say there is some hogging, after that there is some sagging. So for this case, I would say some sort of hogging would be there. So there's some hogging, and after that there is some sagging. So there we say that the 2 points, adjacent 2 points, we can call that part as effective length, and we would say what is the equation we have. We can have a general equation for that particular location of x. For particular location of x, we want to say what is the delta at that location, delta y. So let's apply that load of P. There's some moment developed of M. There is some load of M also. There's some load of M also. There's some load of M also. Let's take this part. So I would say if I cut that section, of M applying a load of P, and there's a moment of M also developed here. There's also a moment of M developed here. I would say that let's take that section. I would say this is mx. and you are at a distance of vertically you are at a distance of let's say this part is y, this is x. So I would write that moment equation mx. So I would write px and p into y anti-clockwise, and your moment m positive clockwise, and minus mx anti-clockwise equals to 0. So mx equals to minus py plus m. So I write that equation of d2y by dx2. That's minus time, that's plus mx by ei. That's minus py plus m by ei. So if I write that in terms of differential equation for the function of y, I would say that d squared plus some, let's keep that equation first, d2y by dx2 plus p by ei of y, and that is also equals to m by ei. So let's have that value of m by ei, m equals to, let's say that m square equals to p by ei, and s square equals to m by ei. So then I would say that there is some solution y equals to y. The solution would be y equals to, let's keep it as d square plus m square y and s square. So we write that equation of y equals to a sine mx plus b cos mx plus s square by m square of x, s square by m square of x. So let's have those boundary conditions. Let's apply the boundary conditions. We have these boundary conditions that delta is 0 at x equals to 0, y is 0. So that means 0 equals to a plus, that is 0, and b into 1 plus 0. So that means b is 0, and x equals to l, delta is 0. So 0 equals to a sine ml plus 0 plus s square by m square into l. So we got this equation that a sine of ml, that is equals to minus times s square by m square of l. And if I say we know theta also, if we know the value of theta also, I would say dy by dx equals to theta. So at x equals to 0, theta is 0. So let's have that equation that firstly we say what is the theta value we can have from this one. That is differentiation of that x, differentiation of that function y. So I would say that is equals to a cos mx into some value of m, and this part is 0, and plus some s square by m square, We say theta is 0. That means you substitute here, that is 0 plus 0 equals to ma cos into 1, that is function of 1, cos 0 is 1, plus s square by m square. So we got that am equals to minus times s square by m square. So if I substitute those values of a and m, we know that value of a, I don't know value of a, but I know value of m, and I know the value of s square by m square. What is the value of s square by m square? Do you know the value of s square by m square? So s square by m square equals to m by ei by p by ei. So value of m by p. So minus times m by p, and your value of m value is equals to p by ei, and m square equals to p by ei. So we got this value also, that's your p by ei under root. So we got this equation that a equals to minus times m by p and root of ei by p. So or we can say your a equals to minus s square by m square and some value of 1 by m. So similarly, if I apply boundary condition that at x equals to l, your theta is 0, theta is also 0. So if I write that equation also, I would say 0 equals to am cos of ml plus s square by m square. So from this equation I can have that am, do I know the value of am from this equation? Yeah. Do I know the value of am from this equation? I know the value of am from this equation, that is s square minus times s square by m square. So I can write 0 equals to minus times s square by m square cos ml plus 1 s square by m square. So we can do that. We can do that here. I would say, let's say that, let's take that equation now. I would say this is your 0 equals to cos of ml, or we can say 0 equals to s square by m square 1 minus cos of ml. That is 0. So finally we got that equation that we got this equation I would say cos of ml equals to 1. Cos of ml equals to 1. On what values of that pi? On what values of pi we say your function cos function is equals to 1. So your values of that, so we say values of cos of 2 pi, cos of 4 pi, 6 pi, 8 pi. That's I would say 2 times n pi. 2 times n pi. So 2 n pi. I would write that ml equals to 2 n pi. ml equals to 2 n pi. ml equals to 2 n pi. So if I say m square l square equals to 4 square, that is 4 n square pi square. So I can write p by ei l square equals to 4 times n square pi square. And I would say what is the value of p now? I would get value of p equals to n square 4 times pi square ei by l square. And if I want to keep it in terms of that Euler's critical load, that is PCR equals to pi square ei by L effective square. So that means if I want to make it in terms of that, let's substitute value of n equals to 1, and let's substitute that L effective changes to L by 2. That means your PCR is equals to pi square ei by L effective square, such that your L effective is equals to L by 2. This is your L by 2. So finally your PCR is also pi square ei by L effective square, but your actual critical load, that means it can take for same length of L. So if you have these two columns of one is your hinge supports, both ends hinged. Let's say both ends are hinged, and both have length of L. That one is your fixed column. Next one is your hinged column. You apply load of P. And there is some reaction upwards also. I would say how much load it can take. I would say it takes load of P1, and this one takes load of P2. I would say P1 would be equals to 4 times P2. Yeah, P1 would be equals to 1 by 4 of P2. That means your P2 should be equals to 4 times P1. That means your second column can take 4 times the load it can take for the first column to undergo that load of, or to that load of critical, that buckling. We can call it as neutral equilibrium. To reach that neutral equilibrium, your column 2 takes 4 times the load it can take for that same length of, for the case of that we call as hinged end conditions. Do you got it? What I'm trying to say? So let's write that statement. That I would write that statement that your fixed column can take 4 times load for the same length of L, to reach that neutral equilibrium, or to reach that critical load, to reach that critical condition as that of pinned column. So that means that's saying that your fixed column can take 4 times the load for the same length of L to reach that neutral critical condition of that buckling, such that as compared to if you are comparing it with that of pinned column. So that's the statement we can have from this equation. So final one is that if the so we got the 3 conditions. Fourth one is that if you have one end is that we call as free, and second end of that column is that free. So this is free, this is fixed. and length is L, you apply load of P. So I would say that it deflects by some, it deflects in this fashion. Let's say it deflects by this fashion, in this fashion. Similarly, if there was one more cantilever here, and it would deflect the same way. So similarly, if I have simply support beam, you apply load of P. So I would say there is some deflection in this fashion. So if I assume this part is as fixed, and then you apply load of that reaction, you apply load of reaction that, so deflection would be in this fashion. So it is similar to that of if there was length of L here, and here the length was 2L, and similarly here the length was 2L. So it's some sort of that the curvature develops similar to that of if you take half of this simply support beam, if you take half of that simply support beam. So if I have that one, I would say this part behaves that there is some deflection. I would say there is some deflection. If I have one more sort of that same sort of that fixed end cantilever, so some sort of that deflection gets developed in this fashion. I would say you treat that, you say there was some cantilever, there was some pin column of length 2L. Now you apply the load of P, and it gets deflected by this by this fashion, that in this fashion. Now such that I would say your effective length is equals to 2 L. Let's have this condition. Let's take this condition. Now. I would say you apply the load of P, and maximum deflection, I can say maximum deflection is some value of A, and you want to go to some value of X. What is that at particular location of X? I want to say what is the deflection that is possible here? What is this deflection that has created? So I would say this part is Y. I would say this part is Y. From the initial position it has reached to some value of Y. I would say at a particular location of X it has reached to some value of Y, but for the moment equilibrium I have to take this part, and this part is equals to A minus Y. The difference between the other section, those conditions, we have that the top was either it was fixed or it was hinged. So based on that, we say there is deflection 0 at that end. At that end there was deflection 0. The deflection was 0 here. But in this case, since it is free, I would say the point itself reaches to some value of delta. It itself reaches to some maximum value of delta. And in the other cases, we had delta somewhere at the mid, maximum, that was maximum here. So delta was maximum at the mid. I assume that. But in this case, delta is maximum at the free end itself. So delta is maximum at the free end itself. We say there is some delta maximum that is equals to A, and we want to go to some value of X, and there we say it has reached to some value of Y. So here the buckling deflection, we say it is equals to Y. And if we take that condition that if I take this section, I would say there's some load of P, and there's some section X, and we have there some moment of Mx, and I would say you apply the summation of moments on that section. So there's some eccentricity of that load P. What is this value? That is A minus Y. If I write that P times A minus Y clockwise, and your moment is also clockwise, or we can keep it in this fashion. Let's keep that as let's assume that moment is in this fashion, mx. I write anti-clockwise moment minus mx equals to 0. So I can say your moment at x equals to pa minus py. So if I use that equation, that ei d2y by dx2. So similarly, I would say d2y by dx2 plus p by ei of y equals to p by ei of a. P by ei of a. So if I have that equation, similarly, I would say you have that equation of I would say your general solution of that equation would become that y equals to a sine mx plus b cos mx, a sine mx plus b cos mx plus that p by ei, and you divide. Actually, is it p by ei? Both we wrote that p by e as at the both ends. Actually, it's P by EI of y, and this one is P by EI of a. So you have this s square by m square. So you write that P by EI, and this one is also P by EI of that, and you multiply that value of a. You multiply that value of a. So you got this equation that y equals to a sine mx plus b cos of mx plus a. That's your general equation, general solution. And at boundary condition that at x equals to L, delta is 0. So that's 0 equals to 0 plus b plus So I got this part now. If I say that at x equals to 0, delta is 0. Is it delta 0? At x equals to 0, at x equals to 0, I would say at x equals to 0, delta is equals to a. Delta is not 0 actually. Delta is not 0. Delta is not 0, delta is equals to a. And this is the difference we say in the other three derivations. This is the difference that at x equals to 0, we say that delta is there, that y value of y equals to a, or delta equals to a. So if I have that equation, so I would say that a equals to, because y is equals to a, so a equals to a sine mx, that is goes to 0 because sine of 0 is 0. So plus b cos of 0, that's 1. So plus a. So I would say b is equals to 0. B equals to 0. Now we got the equation, final equation, that y equals to a sine mx plus a. So now one more thing is that we have one condition that is possible. If I go to that x value equals to L, if I add x equals to L, I would say that theta is 0 here. I would say that theta here is 0. If I have that condition also, theta is 0. So that means dy by dx equals to theta, that is a m cos mx plus we can say 0. So I would say at x equals to L, your theta is 0. So that means 0 equals to am cos ml. So am cos ml equals to 0. So that means your cos of ml is equals to 0, because am cannot be 0. That means entire values of x will have same amount of reflection, that is 0. So that's impossible. I would say cos ml equals to 0. So the cos ml equals to 0. So on what values of that cos function we have, on what values of pi we have that cos function equals to 0. So that is on 2n plus 1 of 2n plus 1 by 2 of pi. That's at pi by 2, 3 pi by 2, 5 pi by 2, so on and so on. So that means 2n plus 1 by 2 and into pi, that equals to 0. So that means that equals to ml. So on ml values of 2n minus 1, 2n plus 1 by 2, 2n plus 1 by 2 into pi. So on that, those values of pi, we have cos functions equals to 0. So finally I would write that if I use that smaller value, what is the smaller value we can have at n equals to n equals to 1. If I have that at n equals to 1, so final value we will say that is 2 plus 1 by 2 pi equals to ml. Yeah, actually the smallest value we can have that n equals to 0. We can take n equals to 0. Smallest value we can take n equals to 0. So on that value we can check. At n equals to 0, we can write 1 by 2 of pi equals to n ml. So if I substitute that in terms of m square, I would say that's your pi square by 4 equals to m square l square. And I know the value of m square, that is a value of m square we are substituting as p by ei. So I would write that p by ei l square equals to pi square by 4. pi square by 4. So that means P equals to pi square EI by 4L square. So if I write it in terms of that critical load, PCR equals to pi square EI by L effective square, that means I have to keep that 4 in with that term of L, pi square EI by L effective square, such that it is also equals to pi square EI by 2L whole square. So that means your effective length of L effective equals to 2 times L. L effective equals to 2 times L. Effective length is equals to 2L. L. Effective length equals to 2L. That's similar to that of that simply support beam with that of a point load at the midspan. Hope you understood those 4 conditions of that end conditions, and how that end condition can change that critical load of that column. So finally, I would say, if there we have 4 end conditions, if there are end conditions of that, first one is that pin it. Next one is that pinned hinged, or we can say pinned fixed. One is pinned and next one is that fixed. Let's say that looks like in this fashion. Third one is that fixed. We say that is fixed. And fourth one is that we have fixed free. Now we say that what is the effective length we have here? Effective length equals to L. Effective length equals to L by root 2. Effective length equals to L by 2. And effective length equals to 2 times L. So if I write that critical load, PCR, so I would say pi square EI by L square, pi square EI by L by root 2 whole square. And here we can write pi square EI by L by 2 whole square. And this one we can write pi square EI by 2L whole square. And if I compare now that pinned column, and one is your fixed free column, you apply load of P. I would say it takes a total load, that how much critical load. Let's say critical load is equals to 100. That means on 100 kilonewton, your that buckling would happen. That is, the buckling would be such that it is in the neutral condition. That means it would reach to some value. After that, it would start that unstable condition. So on 100 values, 100 kilonewton, your critical buckling would start. And if I apply that, I would say on what value of P this column would start critical buckling. On what value of P critical buckling would start. I would say critical buckling would start. That is, neutral equilibrium has reached critical buckling. And that's your critical buckling, or we can say neutral equilibrium. That means if I apply the load of PCR equals to that is actually that 4 times 1/4 of that PCR hinged, because you have 2 square, 1 by 2 square, that means 4 times that 1/4 of that PCR. So if that means you have to apply only 25 kilonewton here. On 25 kilonewton only, your neutral equilibrium would reach. That means on 100 values, 100 kilonewton for this that pinned column, that neutral equilibrium arrives. But for the 25 kilonewton only, your neutral equilibrium arrives for this case. And if I compare now with the this pinned with respect to that of pinned hinged column, I would say on a value of that was equals to L by root 2. So we had the equation L by root 2, that L by root 2. So that means twice. That means on 200 kilonewton, because your L by root 2 whole square, that is actually 2 times some value of PCR. So that's 2 times actually. So 200 kilonewton. On 200 kilonewton, your critical that neutral equilibrium reaches. And if I take that fixed, it was L by L effective was equals to L by 2. So if I have that, that is 2 square, that is 4 times. So 400 kilonewton on 400 kilonewton your neutral equilibrium arrives. Neutral equilibrium arrives. So this is the that definition of that effective length. By varying the effective length, I would say by varying the effective length, your critical load is varies. Critical load also varies. So this is a condition that load is a function of effective length. Load is a function of effective length. It's a function of effective length. So do you got that? Do you got this condition? Now we have the equation yet. We have the general equation PCR equals to pi square EI by L square. Now the thing is that we have a section. We have the section of the column. We have the section of column. I would say there's some width, there's some depth. Actually, it's not depth. It's the other side of that section. Column depth is along the length. I would say there is some length L, and length L is very much for the columns. And we say there's some section which is having the dimensions, lateral dimensions of D cross B. So I would say we have this I value. This is value of moment of inertia of that section. This is the moment of inertia of that section, PCR. So this is the moment of inertia of that section. So which value of I should I take here? Because we have two values, we have two neutral axes, we have two axes. So if I say that this is along X, or it's up to you. Let's say this is X and this is Y. Let's say this is X and this is Y. I would say which value you take. If I calculate Ixx, that would be B d cube by 12. Iyy would be equals to dB cube by 12. So which one should I take? I would take that critical load corresponding to I minimum value. Because if you design for the minimum value of I, that means on the other side of on the other axis, that is already safe. That's already safe. Let's say this value was equals to 100 and this was equals to 200. Some values of 100 and 200. That means in the first case your load was equals to how much load it can take, that's 100 kilonewton, let's assume. And in the second case, it can take 200 kilonewton about y-axis. That means it takes, that means along critical load along x-axis for the buckling to happen along x-axis, about x-axis. So if I write that statement, and you can get the clear picture that if I write that for buckling about x-axis, your P load needed or critical load needed is equals to 100 kilonewton, and for buckling across y-axis, your load needed is equals to 200. So that means y-axis is safe. It's already safe. So if I apply load of 150 kilonewton, let's say I apply design load is 150 kilonewton, that means your y-axis is safe. It won't go under buckling. About this axis there won't be buckling, but about the x-axis there is buckling, because it's going to have a neutral equilibrium only at 100 kilonewton, but your design load is 150. So if you want to design this section, if you want to design a section of that column, I would say you worry about that Ixx. You change this Ixx such that your load can be safely bared. So I would say your critical load is a function of I minimum. So your critical load for the section is pi square EI minimum by L square, L effective square. If I want to say we have that concept of I minimum equals to AR minimum square. If I have this equation, that minimum moment of inertia corresponding to that particular value of a cross section area into some value of R minimum that we call as radius of gyration. So if I have this, I say that there's some axis. Let's say there's some x-axis. I have that dimensions of B cross D. I would say the value of Ixx, we say that I assume that is I minimum. Let's say that's I minimum. let's say that's I minimum, I would say that that's equals to BDQ by 12, BDQ by 12. And I would say, what is the value of area I have? That's BD. Cross-sectional area is BD, and we have some value of R minimum whole square. So if I substitute that means we can get a value of R minimum equals to some value of d by 2 root 2, some value of d by root 12, d by root 12. Similarly, from other side, if the I minimum was along y-axis, if the I minimum, let's say that I minimum was equals to dbq by 12, and that I equate with area into some r square, so your r would be equals to b by root 12, that is some b by 2 root 3. So what is this r means? This r means, this radius of gyration means you have some axis, a reference axis there, you have some axis. You say if the entire area cross section, if this entire area is concentrated on some point A, entire area is concentrated, total area equals to BD. So let's say this area is entirely concentrated on this point. I want to say at what distance of R minimum my moment of inertia would be same about this axis. So we know that minimum moment of inertia, we said that let's take that equals to BDQ by 12, and that if I have that same area that has contributed this amount of BDQ by 12 about this I-axis, I would say how much I want same amount of I about this axis. We have this I-axis, so that would be contributed by that A into what we call as AR square, plus about this axis we say that it's a point, so that we have 0, so we say that this is the definition of that. So your R means radius of gyration means distribution of that area, about some axis, such that it contributes same amount of I minimum equals to AD square. So we got that also. So finally, if I write that equation, that PCR equals to pi square E I minimum by L effective square. So if I substitute the value of I minimum equals to AR minimum whole square, AR minimum square, so I would get pi square E by L effective square. Now one term is that we call as lambda, that is L effective by R. So that is we call it as a slenderness ratio. We call it as a slenderness ratio. So if I convert it in terms of that one, I would get pi square E A divided by L by R whole square. L effective by R minimum, you can call it as R minimum, R square, we can say L by R square. So we got this equation. This is in terms of PCR. If I want to keep it PCR by A, that would give me some value of pi square E by some lambda square, that we can call it as a FCR. So we can get that critical buckling stress, or we can say Euler's critical buckling stress. So that's a function of that pi square E by lambda square. So FCR is function of lambda square. Now we got this equation. That if I write that on what values of lambda, your equation is valid. So I would say that L by R. What does L by R actually means? This means that slenderness ratio, and it's a function of L. So we say that your Euler's buckling theory is valid for long columns. That means there should be some value of lambda. After that, that since your lambda is function of proportional to L, that means there should be some value of L. There would be some value of lambda. After that, your Euler's theory would be applicable. After that, your Euler's theory would be applicable. Since your Euler's equation is valid for long columns, we say it's valid for long columns. So that means we have one more thing, that's L by R, lambda equals to L by R. So we should say for the long columns L is more. So there should be some value of lambda that should be some value of lambda that is maximum. There should be some value of lambda which is some maximum value. So there is a possibility that there might be some limit also. There might be some limit also after that where your Euler's theory is applicable. I want to say that what is that limit? What is that limit? If I plot that variation, if I have this equation that FCR equals to pi square E by lambda square. Now if I write that lambda equals to pi square E by FCR and root. Now if I talk about mild steel, if I talk about mild steel, we have that yield stress of Fy. We have that Fy equals to 250. That is yield stress. And if I want that if I want that critical buckling stress to be yield stress, if I want FCR equals to yield stress, that means I want to use that material up to that yield strength. I don't want that stress is less than FCR. I want to utilize that material to the yield strength also. So such that the material would fail by the action of that material failure, not by the action of material that member failure. So for that, if I substitute the value of FCR equals to Fy, and I use the value of E for the steel, that is 2 into 10 to the power 5 megapascal. So if I use those equations, if I use those values, Fy 250 megapascal, if I use that, I would get some critical load, that slenderness ratio, that is pi square into 2 into 10 to the power 5 megapascal divided by 250 megapascal and under root. So I get a value of I got some value of critical slenderness ratio that is equals to 88.89. So that means on some 88.89 value of that lambda, your Euler's buckling theory is valid. So if I plot the variation between that FCR, and with the lambda, I would say I would get some variation in this fashion. So I get some variation of that. I got some variation, let's say. So there's some variation in this fashion. And we say there's some critical value of lambda. Let's call it as 88.89. After that, your Euler's buckling would not, before this critical lambda, your equation is not valid for those columns. So there should be some value of lambda for the column that should be greater than that 88.89 for this Euler's theory to be applicable. And if this is lesser than 88.89, there would be deviation in that equation. There would be deviation in those results. We can't directly use that equation that for the lambda lesser than that 88.89. And we say that there is a range for those columns also. We call them as that short columns. We say that equation for lambda lesser than 88.89, we say that equation is valid for short columns also. That we can say that stress is not a function of that lambda. We don't say that's valid. We don't say Euler's theory is valid for short. We don't say that for lambda lesser than 88.89 Euler's theory is valid. We don't say that. We don't say that. But what I am saying is that your graph is remains constant. That means at Fy equals to 250 megapascal for mild steel, if you have lambda lesser than 88.89, your FCR is not a function of lambda or length. So we say that now if the column is short, that means if the column is short, your function of that yield stress, that critical stress is not a function of length. Critical stress is not a function of length. Is not a function of length, but we are saying that material is itself failing. Material is failing, not the length of the material, not by the length of the material, but by the material itself it's failing, because we are talking about the short materials. They are failing by the crushing of that material. So that means it does not depend on the length. It does not depend on the length of that, how much length we have. As long as lambda is lesser than 88.89, you can take L equals to 1 meter, you can take L equals to 0.9 meter, you can take whatever length, but you have to ensure lambda is lesser than this one, and you can get that all values of that on Fy, each of those columns will fail. At Fy equals to FCR, your member would fail. That because material is failing, that means entire column is failing. But if you go lambda greater than 88.89, that means there is a variation in this fashion. That means as you increase the L, because lambda is increasing, as you increase the L, your stress is decreasing, because of that instability of that column. It's unable to retain that position. That means it's getting buckled. It gets buckled. So we say as long as you increase L, your FCR goes on decreasing. So that was valid for lambda greater than 88.89. So this is the actual that Euler's buckling theory. So hope you enjoyed that. Now we say that we got this part. Now one more formula is that we call as Rankine formula. Rankine's formula. So the drawback of that Euler's theory is that it's not valid for the short columns. Now Rankine formula is valid for all columns, valid for all. So that means it should encompass all those failures. It should encounter those also, yielding plus buckling. So that means it's valid for all, that is short and long. And actually this is generally used for, this method is generally used for, we call as intermediate columns. Generally we are using it for the intermediate columns. So that means there should be some relation between that that what you call as crushing load. There should be some crushing load PC, and there should be some Euler's load PE, and overall of these that would give me some value of failure load also, combination of those. So there's some equation that connects these three. I write the equation in terms of this one: 1 by P failure equals to 1 by P crushing plus 1 by P Euler's. And I know that crushing, how do you crush something? So that means there should be some compression test, there should be some crushing stress or crushing strength, and if you have that area cross section, that would give you some that crushing load, where your FC is crushing stress, crushing strength in compression, crushing stress or strength, that is in compression, and you have that area of cross section A. So your PC is the we can call it as crushing load. Let's write that as a crushing load, and PE is your Euler's load that you already know, that is PCR, Euler's load, and your PF is your failure load. PF is your failure load. So if I have this equation, I write 1 by PF equals to PE plus PC divided by PC PE. So finally PF equals to PC PE by PE plus PC. Now if I write it in terms of PC only, I would say you have this PC divided by PE by PE plus PC by PE. Then I got that PC by 1 plus PC by PE. So I got this equation. Then if I write that PC in terms of that FC into A, and I have that 1 plus FC into A divided by pi square E I by L square. So I got this equation. So I can simplify it. So I can get a value of FC A by 1 plus do I know this value? What is this value? I equals to AR square. Do I know this value? I equals to AR square. So A by I would be equals to 1 by R square. So that means L by R whole square equals to lambda. So I can get a value of FC by pi square E into lambda square. So I can write the equation that that failure load failure load equals to FCA by 1 plus some value of alpha into lambda square. That is, your alpha is your Rankine's constant. Call it as Rankine's constant. Rankine's constant. That is equals to Fc by pi square E. Fc by pi square E. So we know that material. It would be having some Fc, that is a constant function of that material. Fc. It won't change for the material. Fc is fixed. So E is also fixed for the material, and pi is also fixed. So we can get this constant pi square, that is Fc by pi square E. So we can get an equation of how much failure load it would take that for a particular column, that is equals to Fc into some area of that cross section divided by 1 plus alpha square. So we got this one. We got this one also. And one more thing is that if you talk about if there is long column, if there is long column, and it is subjected to eccentric loading. That means load is not passing through the centroid of the cross section, but it is at some eccentricity E1, E2. That means for this one we have one equation that we call as secant formula. It takes that action of eccentric loading for the long columns. Long column subjected to eccentric loading. For that we use that secant formula, and it's a long formula. It's not in that particular syllabus we have. So we say the general theme is that for long columns, if you have long column, and for larger values of lambda, we say for larger values of lambda, your secant formula is almost tends towards Euler's formula. It's almost similar to that of Euler's formula for larger values of lambda. There's some equation that's bigger. If I write that equation, that is a bigger function, that P by A equals to sigma max by 1 plus ECR. Then we have secant 1 by 2 root of P by EA, then L by R. So there's some function. So let's forget that. So then one more thing is that let's talk about the assumptions we have not touched yet. Let's talk about the assumptions we had in the Euler's theory, but we had not touched those. We say what are the assumptions in the Euler's theory? We derived the equation in the Euler's theory. Let's have the assumptions. We say we only said that load was along the axial line of that cross section. So that means P is entirely axial. P is purely axial. We can write. That means it's not developing any moment. Moment is 0. I would say moment developed is 0 because of P into eccentricity E. It was 0. So this was your first. And material is isotropic homogeneous. That is the every theory starts by this assumption. And third one is that we say that we know valid for long columns, and that means it accounts that buckling failure, not the material failure, but it's not the crushing failure, but the buckling failure is accounted. So that one more thing is that EI of the cross section is uniform, because we used the equation that d2y by dx2 equals to m by EI. So that means EI should remain constant. As long as EI is constant, we can use this equation. Similar to that of deflection of beams, we say if you use that double integration method and that second one was that of Macaulay's. So in those methods also we use the equation EI d2y by dx2. So for that, those also are valid for that when we have prismatic beam. That means EI is uniform. Similarly here we say that EI should be uniform, and we say if you unload the material, axis of that column should remain straight. Column should remain straight. It should not go twisting. It should not undergo twisting. Axis of the column should remain straight. After unloading, axis of column should remain straight. Axis of column should remain straight. So these were the assumptions. These were the assumptions. Okay. So let's take the problems now. Now we are going for the problems now. Let's take the problem. Let's take the problem one. Problem number one. That's you have a column whose cross section is looks like a T section with the dimensions that this is your 100 millimeter, thickness 10, here also 10, and 70 web. Let's say this is 70, and I'm saying that you want to find that buckling load. Find the buckling load. For this, you have a strut. We call that column also a strut. If the length is less, we call that column as a strut. So strut is also a column. This is a column strut. 3 meter length. Length of the column is 3 meter. And this is your T section of the column. That means the column should be in some sort of T section for some length of 3 meter downwards. So this is your 3 meter column. You can have 3 meter column. Then what is going there? We have the material E. Material E is equals to 200 giganewton per meter square, and we have the condition that both the ends are hinged. Both ends of column are hinged. Strut are hinged. Say both ends are hinged. So that means effective length, and we can refer that. We can say that effective length equals to L. That is your length of 3 meter. Length of 3 meter. Now we have this. Remember, we have this section. I want to find that. We want to say what is needed for that critical load. I would say there is some buckling load PCR. That is pi square EI by L effective square. L effective square. So L is also already known to us. L is already known to us. So we got the value of L, and E is also provided. But one thing is that we need to get the value of I minimum, because we have to take that minimum value of moment of inertia of that section. So we need to talk about that section which is having a T section. So we need to calculate I about some, let's say this is some x-axis and there is some y-axis. So we need to calculate ixx and iyy. Let's have those values. Let's take those values. So I would say if I take this iyy, I would say your section is symmetric about iyy. So I can directly calculate that I would say that centroidal axis, that is the centroidal axis about the yy would be along this line, along this axis itself. So I would say iyy of this section, because it is symmetric about yy. So your iy would be calculated directly for these two rectangles. I can have, I would say that is equal to 10 times 100 cubed by 12 plus 70 times 10 cubed by 12. So this is your iyy, that is equals to 839166.67 mm power 4. Now if I want to calculate ixx, I would say we have some centroid. We have some centroid of area. Since for the first case, when we calculate the iyy, centroid of the first rectangle was here on the axis itself, and centroid for the second area was also on the axis itself. So we have not applied some parallel axis form. That area was, because your d was equals to 0, so there was no parallel axis form here. So for the ix-axis, you say there would be some neutral axis. Let's say I want to calculate the value of where would be that neutral axis. I would say where is the centroidal distance from the top. Let's have that value. So for this one, I need to calculate x bar, and that is that's first moment of area divided by total area. That means 100 into 10 into 5 plus 70 into 10 into 35 plus 5, 45, divided by total area, 17, 700. So that value of x bar would be equals to x bar equals to 21.47 millimeter. Now I want to say what is the IXX we have? 21.47. That means if this is 10, there's 21.47 somewhere here. So that's your I, that's your that centroidal axis about that x-axis. I would say that is your centroidal axis about for calculation of IXX. So for the first area, I would say that let's have that IXX now. Let's calculate that IXX. That is equals to 100 into 10 cube by 12 plus area of that 1000 and the distance between the two, between the centroid and centroid of that area and centroidal net centroid of that section. I would say that value, this value would be equals to 5. If you subtract this 5 from the total x bar, so x bar minus 5, x bar minus 5. So x bar is your 21.47 minus 5 whole square. Okay, and second was that one area is also there. That's your rectangle of dimensions 70 cube by 12 into 10 plus 700 into d square. So from this part we say centroid is at 35, centroid is at 35, centroid is at 35, but from this part to the centroid of the entire section, that's at 11.47 whole square. So you can have that value of d also. So you calculate those values also. So your IXX, that comes out to be equals to 952990.2 millimeter power 4. So based on the values of IXX and IYY, you would say what is the smaller value, what is the I minimum we can have? I would say minimum value is corresponds to IYY. So I would use that part of that. I would use that value of I for the equation of PCR equals to pi square value of E 200 giganewton per meter square. 200 giganewton per meter square. Pi square E, then value of IYY, that's your this value divided by L effective square. The value of L effective we would take that because that condition is given that both ends are hinged, that means effective length is equals to L, that is 3 meter. 3 meter. So 3 meter. So you can have that value of PCR, that is equals to 184 kilonewton. Let's take that second problem. Let's take the second problem. So we have a column. We have some column of uniform strength. We have studied beam of uniform strength, and this one is that column of uniform strength. That means stress at each fiber is equals to same. Let's say stress at each fiber equals to sigma naught. Stress at each fiber along the length is equals to sigma naught. That's along the depth, I would say, because column is along the depth. So we say sigma is for each section, sigma is equals to sigma naught, that is constant. So that's we have column of uniform strength. Now there is a area, given, that is area at the top. That's A naught equals to area at the top. And you want the problem says that you want to get the area at the bottom. You need to calculate area at the bottom. And one thing is that you need to account the effect of weight also. Effect of the weight of column is also accounted. The weight of that column, that should be also accounted for this condition. You are applying a load of, let's say for this column, there's some cross section at the top. You are applying a load of P. and that the top area is equals to A naught. So the stresses we developed equals to stress that has developed, that is equals to A sigma naught equals to P by A naught. But sigma naught is entire valid for all values of A. So I don't know the value of A at the bottom. Let's say there is some value of A at the bottom. A, let's call it as A at the bottom. I don't know the value of A at the bottom. And there is some variation. There is some variation of that. I don't know how is the how the variation is there. How the variation of that section is there along the length. I would say, but the area B should be such that, if this load is B, and the weight is also there, weight of the column is also there, I would say the stresses at the bottom should be such that it would give me value of sigma naught, that is equals to some value of weight plus some value of P divided by area at the bottom. So in this situation I have to take, because I would say at each values of x, your load at x changes. So load at any x is a function of load at any, I would say total load at any x is a function of, one is your P, that's constant, comma, that weight at any x. So weight is variable at any x. So you need to take that strip. We have studied that when you calculated the deflection of that bar under the self weight, we said because your P is varying because of self weight, so we need to take that strip and want to take that effect of that strip. So I would say you go to some value of x and you take some strip. Let's take that strip of dimensions dx. You go to some value of x. Let's take some strip. I would say I go to some value of x. There I took some strip dx, and at the top there might be some area of A, and at the bottom there would be some area of A plus dA. It can be negative or it can be positive. I don't know the value of dA. The possibility is that the area can be lesser also. If there is area at the top in this fashion, there is a possibility that area at the bottom would be some smaller value, and there would be some variation. So I don't know this value dA, whether it's increasing or decreasing, I don't know. So but I took it as a value of dA. Let's say there is some value of dA. So the question mentions that effect of weight is also accounted. So I would say for this strip, there would be some weight downwards of W of that strip, and the load is acting from the top P. And so I would say, but the stresses at the top and bottom is equals to same. I would write stresses for this strip, stresses at the top is equals to stresses at the bottom, and that equals to sigma naught. This is the condition in the problem itself, that is a column of uniform strength. I would say what is the area, what is the volume, or what is the weight of the strip? Can you calculate that? So we had some material whose that unit weight is gamma, kilonewton per meter cube. So that is weight upon volume. So I would say the weight of the strip would be some gamma times volume of that strip. So I would say gamma into there, because your area is varying, I can take average area into some strip of dx. So area into length, that's your volume. So but what is the value of average area? I would say gamma into that. At the top I have area of A, and at the bottom I have area of A plus dA, and you divide by 2 into dx. So I have this weight of the strip. So that is gamma times dx into, I would say, what is the value of dA by 2? Can we ignore it with respect to A? A would be some value of, let's say A value would be some value of 100 meters square, and you go to some value of dx such that dx is very less, tending to 0, because you have to take infinite number of strips. I would say dx is almost equal to 0. almost equal to 0, because so that such that I would say there won't be such amount of that deformation, change in area. So I would say this you can negligible, this would be negligible, this would be some 0.01 meter square, let's say, and we can say this is goes to negligible, I would say. So finally you are left with overall value of that weight of strip is almost equals to gamma dx into A. Now if I have that in this equation, that stresses at the top equals to stresses at the bottom, that is equals to sigma naught. If I use that, I would say what is the stress that has developed at the top? I would say at the top there is no load, but there is no weight. I would say there is only a load of P. I would say there is some load of P. Yeah, this is the condition. Now if I say that uh, if I apply the force equilibrium in y direction, if I apply the force equilibrium in y direction, because the structure has to remain in equilibrium, if I apply that summation of Fy equals to 0, if I use that, I would say what is the force at the top? What is the force at the top for this strip? What is the force at the top for this strip? I would say there is some stress developed because of this load P, and I would say and B there, and there is some weight also from the top. There is some weight also from the top, because we have this varying weight. So such that the stresses has reached equals to sigma naught. I would say we have reached some stress sigma naught, and total sigma is acting for this area of A. So this sigma naught is developed because of this load P. So for this top area A, this stresses sigma naught has developed because of P and weight above, because the question mentions that you have to encounter that weight also. So I would say this stress sigma naught has arrived because of this P and weight above. So I would say, but I don't know the value of weight above. So for that calculation, I would say if I apply that summation of Fy goes to 0, I would say sigma naught into A, that should be equals to yeah, that is plus, if I add that strip weight, if I add this strip also plus weight of strip, that should be equals to the load on this part of that strip, on the bottom part of the strip. I would say that value of load would be equals to sigma naught for the area of A plus dA, and yeah, this one. So if I had to make the equilibrium, I would say there is some download load of P plus weight above. There is some load of P plus weight above, such that it causes stress of sigma naught on the top area A, and this is acting downwards, some P net, and because of weight of strip also this acting downwards, and to maintain the equilibrium there would be some net normal reaction. There is some normal reaction of from the bottom some value of P, such that P equals to some P net downwards plus that weight of strip downwards. And if I say what is this value of P, I would say that value of P would be equals to if I have this if I take that part, so that would be that what is the weight of that normal reaction, that is equals to P, and that is equals to actually total load of downward P plus weight of this entire one, plus weight plus I would say P plus weight above. So similarly I have took that here. So now if I calculate this, I would say you're left with weight of strip equals to sigma naught into dA, and weight of strip we calculate it as some value of gamma dx into A, that is sigma naught into dA. Now if I have that variable separable, I would go to dA by A equals to sigma naught by gamma by sigma naught into some dx. So if I integrate it, I would say you go from value of A at the top and you go to some value of a at the bottom that you need to calculate, and you go to some value of x equals to 0 to some value of x equals to L, and we can have that. So I would write ln of a bottom minus ln of a at the top equals to gamma by sigma naught into some value of L. So if I make that equation, I would say ln of a by b, I would write ln of a naught, or I can say ln of a at the bottom divided by ln of a naught equals to gamma by sigma naught into L. So I can write a bottom by a naught equals to e to the power gamma L by sigma naught. So I can say what should be the value at the bottom, that is e gamma L by sigma naught into some factor of area at the top. So you got this equation. So to revise this problem, let's revise this problem. You had provided that stresses at each section along the depth is equals to sigma naught, and you have to encounter the weight or effect of weight also. So you are applying a load of P from the top on area of A naught such that your stresses P by A naught equals to sigma naught. And similarly, there is some variation of that section along the depth such that area at the bottom, that is equals to some value we don't know, and you want to say what is that, because your weight is vary, because you have to take the weight of that column also. So I would say at each values of x, your weight is varying. So you take that strip of dx, you said that on this strip, there's some load acting from the top, and you have to balance those weights. I would say there's some load of P acting downwards, and there's some weight of that weight above also. So this weight also is there, weight above, and that we call as weight above. So there's some net value of P plus weight above such that it causes stress of P plus weight above divided by area at the top. We said that area at the top was some value of A, and it would cause a stress of sigma naught. And if I have that weight of the strip also, that is acting downwards, I would say there would be some normal reaction upwards, some n. If I have that force equilibrium, I would say P plus weight above for the area of A, P plus weight above plus weight of strip, that should be equals to normal reaction. But I know one thing that P plus weight above is, if I convert it in terms of stress, that I know that stress should be constant. So if I write that sigma naught into some value of A, that plus I would write weight of strip was equals to, I calculated that equals to gamma dx into A, and gamma dx into A, that should be equals to some normal reaction. And I don't know the value of n, but one thing is that I know the area here. I say that area here is A plus dA, and the stresses developed here is also sigma naught. And based on this one, I derived this equation. Now we say that let's talk about that PCR for different end conditions. PCR, critical load, buckling load for different end conditions. First thing is that you had this column of length L, and you apply a load of P, and there is a spring also attached at the top. Now, how do you calculate that PCR value? I would say there is some spring of stiffness K. Now, how can you calculate this? So I would say because of that load, there would be development of buckling. So let's say that you displace that column by delta at the top, by amount of delta. Let's say that column has arrived to some value of some delta here from the original delta, such that load P is reached here. So it has reached here, but because from this side we have spring that is fixed, so there is a possibility if there is delta, if the column goes delta on this side, that means there is possibility of that compression in the spring. So that means on the spring itself, there will be development of compressive force F in the spring. So same would get transferred on that column also, Fs. So it would also get shortened by that same amount of delta. So I would write, this is the compatibility also, I would write delta developed delta in because of buckling. It is also delta because of buckling is also equals to delta in the spring. Now there is some point O. Let's say there is some point O. If I apply equilibrium of those moments, summation of moments about point O equals to 0, I would say some Fs into L, that is that's anti-clockwise about the point O, and plus P into delta, that is equals to 0. Okay, and I know one thing, that what is the value of that delta? Do I know the value of Fs? Can you write that Fs is equals to some stiffness K into delta? Can you write that? Because of this, I would say minus times K into delta into L, plus that is equals to P into L, P into delta. So finally I would write that critical load for this column would be equals to K by or KL. So we got this equation, PCR equals to KL. Now similar problem we can take for this. We have the same column of length L. You apply a load of P. We have two springs now attached. Let's say this is spring 1, and there is one more spring. Let's say that is spring K2, and you just displace this. You displace this what we call as column either of the side. Let's say it displaces. You displace it to this side such that now the configuration would look like in this fashion. So there is some delta of that delta because of buckling. So P has reached here. That means your spring K1 has shortened by amount of delta. So your force in the spring 1 would be equals to K1 into that same value of delta. And if this point, because you have to maintain that rigid conjunction also. If this point P has reached to some value of that's at delta, so that means this spring has got elongated by same amount of delta, such that this point would reach somewhere here, and this point would reach to this point. So I would say this point, that spring has reached here, that point A has reached here. This is your point A, and let's say this is your A, B, A. Let's say this is your A, B, C. Let's have that one more time. I would say you had this spring. So there was some column, and I would say this is your A, this is B, this is C, this is D, this is, let's say this is E, and you are applying a load of P here. I would say if you displace that point C to either of the side, that means we said if we deflect it to some point of, let's say to some point of that's at delta. Let's assume that it's at a delta. So point C has reached here. I would say this from this side it can't go anywhere. Point A can't go anywhere. Point A would remain here, but that means your spring is getting that elongated. That spring has got elongated such that your point B is here and point C is here. That means there is delta elongation in the spring what we call as K2. In the spring K2, in the spring 2, we had elongation delta equals to total delta elongation equals to delta. And from this side, I would say this point, if this point C has reached here, that means from this side point E is already there. It won't go anywhere. So that means in this part there is a compression of that spring. There is compression of that spring. And finally, I would say there is delta compression in the spring that is equals to delta. So finally, if I have that free body diagram of that column, I would say initially the column was in this fashion. It has reached to some value of at a distance of delta. I would say there is some P, and there would be some compressive reaction Fs1, and from this side also there would be some Fs2, in the opposite direction, because yeah, because in this spring there would be some development of tensile force Fs1, and in the other spring there will be development of compressive force Fs1. So if I apply that summation of moments about this point O, I can write Fs1 and Fs2, they are in the same direction. That is anti-clockwise about the point O. Fs1 plus Fs2 into length of L plus some moment of P into delta, that is equals to 0. And I know that value of Fs, we know that spring force is equals to K times delta. I would say minus times, or we can say, which implies that K1 delta plus K2 delta into L equals to P into delta. Then I can write K1 plus K2 of L equals to some PCR. That's your answer. Let's take one more problem. Let's take the spring, that's your torsional spring. There is some column of length L. You apply a load of P, and from the bottom we have some torsional spring. We call it as torsional spring. So this would prevent theta. That means this would prevent theta. This would try to prevent It tries to prevent theta. So I would say initially for this spring, linear spring, this was your linear spring, and this one is your torsional spring. So for the linear spring, we say the force developed in the spring is equals to K times K linear. We call it as K linear into some delta, linear displacement. And for this one, we say that torsional force or torsional force, we can say torsional force, let's call it as Ft. Ft is equals to some torsional that we call as torsional stiffness. Yeah, this is your torsional stiffness into some theta. So it would try to prevent that theta. So there is some development of torque, or we can say torque force, whatever you can say. Torque is equals to K times theta. Okay. Now it would try to prevent that theta. So if I say your column from this side, it would go to anywhere, but it would develop some theta, and based on that theta, it won't get linear stretching or contraction, but it would go under some theta. Because of that theta, it would have some force developed that is equals to Kt times theta. So there is some theta developed here, and I would say that point P has reached here, and there is some delta developed for the length of L. If I write that summation about this point O, that summation of moments about this point O equals to 0, I would write P into delta. That should be equals to some Kt into theta. P into delta should be equals to K times theta. And if I write that for smaller values of theta, I can write that delta equals to L theta. That tan theta equals to perpendicular to base. That means delta is almost equals to L theta. So I can write L theta equals to Kt times theta into P. So we can write P equals to Kt by L. So that means it registers what? It is developing a value of some value of torque. So this value is some values of torque, that is kilonewton meter, and torsional stiffness would be in terms of kilonewton meter. So finally there would be some PCR, that is kilonewton meter per meter, that is your kilonewton. So your torsional stiffness is having a unit of kilonewton meter, and the force that has developed is actually a torque. It's actually a twisting moment or torque. It can resist. So because of that torque, you are preventing some theta. Now, if you take that similar case, for that L by 2, L by 2. Now what we do, one thing, we have the torsional stiffness at the spring at the mid of this column. You apply load of P, so what's happening, I would say the theta would be developed, I would say it would go some fashion, in this fashion. It would go some sort of deflection in this fashion. Let's say the theta developed here is theta, and here also some theta, so such that this external here would be 2 theta. So your spring is resisting 2 theta. Finally, I would say spring is resisting, trying to resist 2 theta. So if you have this equilibrium, if I say that this is your P, and this point has reached here, and there is some stiffness, torsional stiffness of KT, and it's preventing how much theta? 2 theta. So this is your L by 2, and this part is theta. This is some values of, let's approximate it equals to L by 2 theta, because we are dealing with small theta. So this will be equals to L by 2 theta. If I have that equation, now if I write that P times L by 2 theta, P times that delta, because your delta equals to L by 2 theta, that is equals to K times KT times 2 theta. So finally I would write P equals to 4 times KT by L. So your PCR equals to 4 times KT by L. Now if I have that, I would say there is some, we call it that rigid beam ABC. We have this ABC, and it is we can say it is hinged and at the both ends, and there is some stiffness, there is some spring of torsional spring, and I would say if the beam is rigid, I would say EI is infinite, and there is some spring of stiffness, torsional stiffness KT. If the beam is rigid, that means EI of the beam is infinite, and you are applying a load of P at this point P. You are applying a load of P at this point B. So what is going to happen? How can you solve this problem? So your EI is infinite. What does this mean? That means would there be any curvature? Would there be any curvature? Would there be any curvature? We have the equation that 1 by R equals to M by EI. If there was some beam, you applied load of P, I would say there was some deflection at the midspan, PL cubed by 48 EI. So there was some effect of EI. If the EI is such that it is infinite, that means your delta is equals to 0. That means it would behave as a rigid. Remember, there won't be deflection. So I would say that if the ABC is not going anywhere, that means the external work done because of that load P, external work done because of that P by P, that should be converted into the strain energy stored in the spring. Can we say that? The external work done by P, that should be stored in the spring. So I would say, if I say that, I would say, let's say it has gone, because your beam is rigid, ABC is rigid, that means it won't go any deflection. There won't be any deflection, but I would say it would remain as a straight member. And at the midspan we have attached a spring. Here. So I would say the delta developed here, it's developed because there is some spring. Had there been no spring at the midspan, there would not have been any deflection, because your point A and point C are at the same level. So finally your B had only one option, that is to remain at the level itself. So it would have been the profile would have been in this fashion. But your spring is there, that means there would be rotation would be allowed. A rotation of that member would be allowed. So I would say there is some theta developed, and it is theta is constant for this length A, and there is also some theta developed because your length is same. You can take this length LL. So your L is same. That means theta developed is also same. And I would say there is some 2 theta that is contributed by that spring of stiffness KT. I would say you are applying a load of P here, so that work done because of that load, I would say that work done is 1/2 P into delta. If the load is gradual, delta developed would be also gradual. So that's why we write 1/2. That's gradual. Area of that curve 1/2 P into delta, and that should be equals to strain energy stored in the spring. We know that we have this equation 1/2 P into delta. What is the strain energy stored in the spring? Do you know that? Half of kx square. Similarly here I would write 1/2 P into delta. If I replace that P in by the force in the spring, I would write force in the spring into delta. So that I would say, what is the value of F? That is some K into some delta into delta. So I would get a value of K delta square. Similarly, if there is a torsional spring, I would say there would be equation that strain energy stored equals to half of K torsional spring, torsional stiffness into some theta square, because your torsional stiffness is preventing or undergoing some theta. So I can use that equation 1/2 K2 theta square. So what is there we can get? Can we get the value of delta here? So I would say that some delta has developed, and that is equals to L times theta. So 1/2 P into L into theta. That is 1/2 KT into theta square. So I can have that equation of theta, that theta at the equilibrium. That means when P has reached from 0 to some value of, when the load has reached to some value of from 0 to P, final value of P. So I would say theta equals to some PL by KT. Do we got this? Theta equals to PL by KT. PL by KT. Yeah, actually, if we see that how much theta we have here because of torsional stiffness, how much theta we had here? Actually, we had that 2 theta. This part is contributing theta, and this part is also contributing theta. So 2 theta we have developed for the torsional stiffness. So 2 theta, we have to write that function of 2 theta. So this one should be in terms of 2 theta whole square. So finally it becomes equals to 1/2 KT into 4 theta square. So we can write that that theta equals to PL by 4 KT. Let's say that the one thing we studied earlier, that was your double bow condition. That was in this fashion, some sort of in this fashion. So we say that at n equals to 2, your value of PCR was equals to pi square EI by L square, and this was equals to 4 times because your n is equals to. Now, on similar grounds, I would take some problem that is in this fashion. We had this column of length 2L. Now I have installed we call it as a bracing. There is some bracing. So there is some bracing. We can call this part as a bracing. So initially, if there was no bracing initially, I would say the profile would have been in this fashion. There was some column of length 2L, and in this part, so deflection would have been in this fashion. I would say that L effective would have been 2L by root 2. Now for this case, because you have applied some restraint here, that means here the theta would be 0, the delta would be 0. So that means so we have 2 columns now. We can assume that we have 2 columns now. We can say there is some effective length 1, L effective 1, that is L by root 2, and there is some one more effective length 2, that is equals to L. So if I write that, how much load you are applying a load of P at the top. How much load would be there? P1. How much load would be there? That is critical load for 1. That to cause that critical buckling, I would say that would be equals to pi square E I by L by root 2 whole square. And for the second column we have, that is equals to pi square EI by L square. So this value would be some 200 kilonewton. This would be 100 kilonewton. So which one should you prefer now? Which critical load you should take for the entire? If you want to design this entire column, which load should you take for the design? I would say you should take P2 for the design, because your P2 is lesser. So critical load PC2 or PCR2 would be lesser. So you design if you design this condition, if you design for this condition at an effective length of, at the rate of effective length equals to L. So if this is safe, that means the upper part is also safe. Similarly, if you take that same problem with different that lengths, with different length of those columns. So you have this bracing here, you have this bracing here, and there's some length L1. Here we have a length of L2. I would say for this one, I would write P1 equals to pi square EI by L1 square. And that's actually, it's not L1 square, that is effective length, and effective length equals to L1 by root 2 whole square. For the P2, we write it is some sort of simply support or pinned. It's some sort of pinned. I would say that is equals to pi square EI by L2 square. Now it depends on the length of values of L, L1 and L2. Accordingly, we can get, let's say, if P1 equals to, if P1 is greater than P2, that means critical load would be, which one would be critical? P2 would be critical. That means overall effective length of the structure would be L2. And if P1 was lesser than P2, that means critical would have been P1. And at that rate, you have to take effective length of L by root 2. Similarly, if you have this spring, we talked about this one. We talk about this one, that both ends are hinged. Here the theta was 0, here the theta was 0, and there was here also moment 0, m is 0 here, m is 0. So effective length was equals to L by 2. Now you do one thing, you don't use those supports, you use those torsional those springs, torsional springs. So whose value of KT? If you say that KT is almost infinite, if the KT is infinite, I would say, what is the equation for that torque developed in the spring? That is KT times theta. Now, if I say how much theta has been developed, I would say that is equals to some T divided by KT. But if your KT is that infinite, if your spring is such that it has a stiffness of infinite, I would say your theta developed equals to 0. That is similar to that of a fixed beam, fixed column. That is similar to that of a fixed column. That means your effective length would be, equals to L by 2 for this case. That if the both those springs have KT equals to infinite. So one thing is that if you have three columns, this is the cross section of 3 columns. Now we had 2 cases. One is that they act independently. And second one is that they acted together. If they acted together, you need to say what is the PCR for the first condition, PCR1. That means that would be 3 times P1. So I would say that one of the cross section, one of that column would take some load of P1, and if you multiply that 3 times, so you would get a value of PCR for that group. So that is 3 times pi square E by L square, and you have that pi d power 4 by 64. Now second one is that if they act together, if they act together. So that means the neutral axis would be one single neutral axis would be there. Single neutral axis. So let's say the centroid of this one would be here, centroid of this one would be here, centroid for the third one is here. Now we have two possibilities that so finally we say for the P2, I would say for the PCR2, that is equals to pi square E I of the combination of the combined, but that should be minimum divided by L square. So what should be the value of I combined minimum? Along which axis you should take? If I say there are two possibilities, if I take that combined effect about this axis, so if I take this x-axis, if I write this as a y-axis, let's say this is some y-axis, this is some y-axis. If I say what is the value of I, y, y combined? I would say you have that third column is on that line, that is centroid of that third column is along that line. I would say you have that 3 times pi d power 4 by 64 about their own centroidal axis, and plus about their this was your 3 times pi d power 4 by 64. This was about their own centroidal point, centroid, and you have to use that parallel axis theorem plus a some value of a d square, because for this and this your d is same, that is d is equals to some diameter by 2, so let's say this is some d dash, so d dash square, so d dash equals to some diameter by 2. So you have to use parallel axis theorem how much times? I would say 2 times parallel axis theorem, 2 parallel axis theorem. Now if you want to take about one more axis that is along this way, there would be combined net centroidal axis about along the x-axis. I would say a net value of that would be somewhere here. So you have to use, for this case, you have to use 3 times centroidal parallel axis theorem. So there would be some value of d1, there would be some value of d2, and there would be some value of d2. So you have to use 3 times parallel axis theorem. So if I take that, what should be the value of I, y, y combined? That should be minimum. You should prefer this one. You should take this value. Let's take a simple problem that you have this column of length 10 meter column, and you have one bracket attached here at 4 meter from the top, and let's say this is let's say this is AB, and there's some eccentricity of that load P from this point C. So you need to say draw shear force diagram, bending moment diagram, and axial force diagram for this column AB. Column. I would say if you want to transfer the effect of this P, I would say there's some P developed here, and there would be some MPE developed also here. So if I say there's some PE, there is some load of P downwards, and we have some supports A and B. So how can you make the shear force diagram? Can you make the shear force diagram subjected to that moment of PE? I would say the reactions would be developed in this fashion. I would say reactions developed would be in this fashion, that this would give you this was your 6 meter, this was your 4 meter. Do you know that what is the reaction developed because of that moment? M by L upwards, M by L. So here the reaction developed would be PE by 10, and here it would be PE by 10 upwards. So if I make the SFD, I would say there is some downward decrease of 0.1 PE, and it would remain constant throughout the length, and it would increase finally. So 0.1 PE is your SFD, negative. If you want to draw the BMD, I would say up to this point, what is the area of the SFD? That is 0.1 PE into 6, that is 0.6 PE, negative BMD. And after that, there is a clockwise moment of PE, so it would increase such that final value is equals to 0.6, that is PE minus 0.6 PE, that is 0.4 PE. And area between these 2 points is also 0.4 PE. Finally, you can join that. So this is your positive and negative BMD. Now for the third case, for the axial force diagram, For the axial force diagram, there is a load of P. There is a load of P here, and we have some support here. We have some support at B. We have some support at point A, and this length is 4 meters. This length is 6 meters. And how can you get those reactions A and B along the axial line of that member? If I say that, do you know any compatibility here? We have this hinged support, and we have this hinged support also. Can you say delta total for AB equals to 0? Can you say? So if I make the free body diagram, let's say that this is your free body diagram. I would say you are applying a P here. That means there should be some upwards A reaction at A. Let's call it as a reaction at A. Reaction at A. And similarly, there should be some reaction at B also upwards. Let's assume that reaction B is also upwards. Now, if I make the free body diagram, I would say you have this line. There is some reaction RA upwards. Here it should be up. It should be downwards. And for the second case, this was your 6 meter. This was your 4 meter. I would say for the 4 meter length, you have this RA upwards, and there is one more load that is PA downwards. That is P downwards, and there should be net value. Let's say that net value is upwards P minus RA based on this direction. If this is downwards, that means you have to show from this side also upwards, such that it is net tensile. So if I use that, I would say total delta is total equals to 0. That is equals to RA L by AE plus, and that is compressive. For the first case, that is compressive, and second case, that is tensile. So RAL by AE plus P minus RA L by AE. That should be equals to 0. So I would write 6 times RA plus 4 times RA equals to 4 times P, such that RA equals to 0.4 times P, and RB would be equals to 0.6 P. So that means the direction you assumed for the RA is positive. That means the direction for the RB is positive. That is correct. So if I have this direction of that RB, RA, that is tensile, that is compressive 0.4 P. And if I want to make that, what is the value of this one? I would say there's some net value of RA minus, there's some net value of P minus RA, that's 0.6 tensile, 0.6 tensile. And initially I assumed that the direction of P is also upwards. So direction for this one, that is tensile. Now to make the combined axial force diagram, I would say this was your line, this was your column. In the first part, there is positive tensile of 0.6 P, and in the next case we have compressive of minus 0.4 P, not PE, this is P. Okay, this is your axial force diagram. So let's take one more problem. So we had a section of the column. This is the section of column. So this is the top view of the column, section of column. There's some point A. At the corner. And what's the problem saying? Problem is saying that stresses at the farthest point, that is A, stresses at A that is in the first quadrant. I would say we have 4 quadrants. That the stresses in the first quadrant at A, that should be equals to 0 because of load P in the third quadrant. That means load should be somewhere in the third quadrant. This is your first quadrant. This is your third quadrant. Load should be somewhere here in the third quadrant. There should be some load P in the third quadrant, such that it would cause a stress of sigma, net value of sigma at A equals to 0. You need to get that equation. get the equation for that. You need to get the equation for that. You need to get the equation for that. Let's say this is some x line and this is some y line. Then we need to get equation, some sort of equation of x comma y. I would say this load p is somewhere at some distance of x from this reference line of y, and it's at some distance of y from the x line. So it has the coordinates of, so the load has coordinates of x comma y. You want to write the equation of that that x comma y for the stress at point A to be 0. Now if I want to make that, I would say you transfer the effect of that force P onto the centroid, and you want to have that effect of moments also about these two axes. So if I write that also, let's say this is your reference x line, and your load is here somewhere. So that means a hogging moment has been developed in this fashion. Moment of P into y about this axis. So that means neutral axis would be some sort of x-axis for this moment. Neutral axis is also same. And if I know that you are applying a moment of, you're applying in this fashion a moment. Actually, the direction of moment is not in this way. Direction of moment is not in this way. So your point is below, your load is below that reference, I would say, x line. So your moment P is P into y, that's causing this moment. That's causing in this fashion. So I would say anti-clockwise moment. So in this fashion. So if I would say, if there is some section and you are applying P on this section from this side and from this side, I would say about this section you're applying a load, you're applying a moment in this fashion, so such that it causes negative hogging moment. So I would say top members would get tensile stresses, bottom would get compressive stresses. So at the top we had point A. At the top we had point A. So at the top we had point A because it is at the top fiber line. So at the point A, your stresses is tensile positive, and that value equals to Py. This is your my by ixx into some value of y. What should be the value of y it can have? So initially it was y value, and it can have y equals to y max, some value of y max. And if I take the dimensions of that b into d, if I say this is some b, if I say the width is b and depth, I would say depth of that section is d, so that y maximum would be equals to d by 2. And if I calculate ixx also, can you calculate those values? I would say that is equals to p times y. Some y max would be equals to b by 2, and ixx would be equals to b dq by 12. So you are left with some value of 6 times some moment of py divided by bd square. So you got this stress 1. Let's call it as stress 1. And similarly, if you transfer the effect of that moment about the line yy, you have this yy line, and your moment is somewhere here. This load is here and at a distance of x. So because of this one, your moment that is getting developed, that's in this fashion. That's anti-clockwise. So why do we rigid? Why do we have rigid? So if you want to transfer that effect of that p about that y axis, I would say your point p is at this point from the reference line. So it's causing a moment of in this fashion about this line. So the direction of arrow would be in this way, not the direction I have shown. So direction of arrow would be in this way, anti-clockwise. Yeah, in the clockwise manner. So a moment in this fashion, I would say. So I would say if the neutral axis forms about y axis, so this is your neutral axis, I would say. So if this is the neutral axis, that means the fibers, that means these fibers would have, that means here the stress would be 0. And if you talk about the point A, that would be having tensile stress of that is P into X and some value of X max divided by Iyy. So there is some value of X about the y axis, and if you talk about what should be the value of X max, that would be some value of yeah. In the first case, if you took the first case, I would say the y maximum here was, actually we are talking about the y max. Here the y max was along this one. So y max we would have d by 2. So this would have been d by 2. So y max would have been d by 2. Y max would have been d by 2. Such that finally you would get this equation. And for this one, x max would be b by 2. So x maximum would be equals to b by 2. So if I calculate that also, I would say some px into b by 2 divided by, what is the Iyy we have of that section? That is, it's cutting this line. Y axis is cutting this b, so that is dbq by 12. dbq by 12. So finally we got some value of that stress equals to px and some value of db square 6 times. So we got this equation also. And third one is that, and third one we can take db square. And third one we can take the direct axial, if the load was directly on the on that point, that is centroidal point. If the load was directly here, that means you would have a uniform stress of, that means each and every point would have stress of sigma equals to sigma axial, that is P by A, that is compressive, minus P by A, that's minus P by pi d squared by 4. Sorry, this one is your BD, minus P by BD. This one is your compressive. So finally, I would have an equation that stresses at that point corner A, that should be equals to 0. This is the condition I have to satisfy. Stresses at that A should be equals to 0. Okay. So we have this stress of positive here at the point A. On this point also we have stresses positive tensile. So on these fibers we have stresses tensile positive. So I would write 6px. I would write 6px by db square. 6px by db square. And second one was that of 6py by bd square. 6py by bd square. That is 6py by bd square. These two are tensile. And if you talk about that axial stress, that is minus p by bd and minus p by bd. And net of these three, that should be equals to 0. Net should be equals to 0. So if we remove this part, b by dd, p by bd, p by bd, p by bd from entire 3, I would say I would get value of 6x by b plus 6y by d minus 1 equals to 0. So such that I would say 6x by b plus 6y by d equals to 1. So this is your equation of that point. Equation of that, if your load was in the third quadrant, add some value of x and y. I want that stress at A equals to 0, and this is your equation. If you substitute that, you want to say I want stresses at point A to be 0. If I substitute value of x equals to 1, what should be the value of y such that overall stresses at A equals to 0? This is your equation for that. Now let's take one more problem. You have to use that Rankine formula. It's saying that use the Rankine's formula. Do you know that Rankine's formula? What that is? P failure equals to FCA 1 by divided by 1 plus alpha lambda square. Now Now we have a long column that is 1.5 meter column. Length of the column is 1.5, and cross section of that, we have circular cross section of the column, phi equals to 50 millimeter, and Fc of the material is 560 megapascal in the compression. In the compression, we have stress of 560, and we have to use that factor of safety equals to 3. Factor of safety equals to 3, and alpha equals to 1 by 1600. Alpha equals to 1 by 1600, and you have that. If the we have two cases. If the column was pinned, if both the ends are pinned, then you have to say what is the value of PCR, or we can say P failure load. And if one was fixed, one was fixed free condition. For this condition and for the other condition, we have to say what is the failure load we have to have. Or actually, if you're talking about that, we have factor of safety also. So if there is some failure load and you divide by factor of safety, so you can get a safe load we can have. So the question is saying get the safe load. I would say what should be the load that is safe for these conditions. Be safe. So if you take that first condition, that free, or we say pinned condition, hinged condition, that means I write the equation P safe would be equals to P failure by factor of safety. That is some value of Fc. What is the value of Fc? We have 560 megapascal. 560 megapascal. And area of cross section. Area cross section would be pi d square by 4, pi 50 square by 4. Pi 50 square by 4. Pi. Actually, is it equation of Fc? Yeah. Pi by 4 of 50 square mm square divided by 1 plus alpha. Alpha value was equals to 1 by 1600. 1 by 1600. 1 by 1600 into lambda square. So what is the value of lambda? What is the value of lambda for hinged condition? Lambda equals to L effective by R minimum. And for the case 1, your effective length equals to L, that is your 1500 millimeter, and your R would be equals to I by A, that's your pi d power 4 by 64 and pi d square by 4, that's your d square by 16. So R is equals to d square by 16. So this is the equation that R square equals to I by A. So it's such that R square equals to d square by 16, which implies R equals to d by 4. R equals to d by 4. So I can use that values, that 1500 and d by 4. 1500 and d by 4. Okay. 1500 and d by 4. 1500 and d by 4. 50 by 4. This is your millimeter. This is also millimeter. And you have that square, lambda square. This was your failure load. You divide by factor of safety. That's your factor of safety of 3. Factor of safety equals to 3. And you would get a load such that is safe for that hinged condition. Some Newton, some kilonewton, whatever. And if you take that second case was that fixed free, and the parameters are same except that of a effective length is only varying. The rest of that data is same. For the two cases, rest of the data is same. We have that equation Fc A by 1 plus alpha lambda square. So each of these terms is the same except that of effective length is varying, and you divide by factor of safety also. Divided by factor of safety. So only that L effective is changing. Do you know what is the L effective for fixed free? That is twice L. Do we know that? Do you know that L effective is equals to L? L effective equals to L. If you use that value only, so I would say for the second case, I would write. Now for the second case, if you are talking about for the second case, that is fixed free. So first part you are over with. Next part is that if you're talking about fixed free, you would say you have that FC A, and you have that factor of safety also. 1 plus alpha is also there, and you have L by R. You have to only change that L by R equals to 2 times L by R, 2 times L by R, such that it becomes 3000. 3000. Yeah, this is the final equation, and we would get an answer of, we would get some value that's 9905.92 Newton. This is your answer for the second case. Let's take that one more. Let's take one more problem. So we have some section, cross section of that column, and you are applying a load of P, and it is subjected to moment also. Because of PE, there is moment also developed PE. So there's some cross section, and after that, after the column is ending, after the column ends, it is resting on that, we call that as a base of column. So there's some base of column, you are looking from the that side view. So this is some base of column, and it might have some dimensions. It might have some dimension of BD. It might have some dimensions of BD. So there is some point A on this side, and there's some point B on this side. I want to say you have to calculate the stresses at the B, stresses at A and stresses at B. That is the final stresses because of these two loads P and M. I would say because of the P on this entire cross section of that's of the base, we have uniform stress P by A. That is axial. So stresses at A is also, that means stresses at A and B would be same because of that axial stress. Because of that axial force P, that would be having a uniform stress of minus times P by A, area cross section. And next one is that you are applying a moment M. So there would be some axis. Let's say there would be some axis about which this moment is acting, M. So that is that for the point A, there will be development of tensile stresses. So there will be development of tensile stresses from this side A. So A side is from this one, and B side is from this one. So there is development of tensile stresses from from the side A, and compressive stresses from the side B. So they are, point A is on the extreme. So that means point A is having a stress of sigma because of bending equals to M y by I, y max by I. And similarly from this side we have that it would have stresses M y max by I, but one is compressive, next one is that tensile stress. Now the condition is that the problem says that the stresses because of bearing, that we also call as bearing stress, or we can say direct axial stress, that we have represented as sigma A. So sigma A, that is, it's saying that sigma A is equals to that because of bending, sigma B. It's saying that sigma A equals to sigma bending. If the question says that the maximum bending stress we can have, this is your maximum bending stress. So you can write maximum bending stress. Problem says that maximum bending stress equals to maximum bearing stress. If you use those equations, and you need to say what is the net stresses at point A and what is the net stresses at point B, sigma A net and sigma B net. You need to say what are the two values we have. Now, if I write that, if I say initially the, where it has reached, yeah, we have this one. So initially the stresses, I would say because of direct axial stress, we have, I have that stresses at A because of direct axial stress, that equals to minus P by A, and because of direct axial stress, stresses at B is also minus P by A. But stresses because of bending at A equals to positive My by I, and that's Y max. And stresses at point B, stress because of bending about point B, that is minus times My max by I. But the problem is saying that P by A is also equals to My by I. So if this is equals to this, so what we get, if this P by A is equals to My by I, so I would say sigma at A finally would be equals to minus times P by A plus times your value of P by A, because this is positive and overall value of this one is also P by A. And sigma at B would be equals to minus times P by A, and minus times you also have P by A. So finally you would say stresses developed at A equals to 0, stresses developed at B equals to minus 2 P by A. So compressive stresses. So maximum, I can say maximum stresses we have, that's at point B. So if I pull out the variation between the 2 points, I would say initially the stress variation was that this was your compressive, compressive minus P by A for the entire section, and after that you had tensile of My by I, such that net value is equals to net value of that diagram, stress at A equals to 0, and here we have 2P by A. Then we have linear variation. So this is your tensile, that compressive stress net value of minus 2P by A. So let's take one more problem. This we call as the current of column, current of circular column, or current, or we can call it as core of circular column. So we say that so there's some column of cross section, there's some cross section. Now you applied a load. If the load was applied on the centroid of the cross section, that means there would have been only axial stresses, that is P by area cross section, and the stresses would have been uniform for the entire cross section, uniform stresses. But if the load is at some eccentricity, now if you say there is some line and load is not at the center, it's at some eccentricity of E. If the load is at some eccentricity of E, we know that on one of the sides there would be compressive, and on one of the sides there would be that tensile stresses because of that moment developed P into E. So I am saying that I want net compressive stresses throughout that cross section. I want net compressive stresses at each point on cross section, and each point on cross section. So what should be the condition for that? How should I get that? That means I want that net tensile stresses should not be there. There should not be net tensile stresses. Net tensile stresses should not be there anywhere. Should not be there. Or we can write should not be anywhere. Should not be anywhere. So for this condition to happen, I would say that net value of sigma anywhere, that should be less than or equal to 0, because your compressive is negative. So I would say net value of sigma should be less than or equal to 0 at any point of that cross section. And for that, you have to keep the load in such a way so there should be some value of E such that it would give you that there should be some value of E for that your value. So I would say there should be some eccentricity that would cause stresses less than or equal to 0 at any particular point. So when we say that there is a development of that, when you calculate that, there is some development of that core. If you place that load in that span only, in that part only, that means net overall, you take any point inside anywhere on the cross section, you take any point anywhere on the cross section. Now the development of the stresses would be such that stresses at that point A net would be equals to less than or equal to 0, such that no tensile stresses net would be there. So we had to get that equation of that eccentricity E. So let's say that, let's have that column. Let's say there's some column, and there's some reference line, and this is some center, and the load P is somewhere. Let's say this is some center, and load P is acting here. Load P is acting here at some eccentricity E. I would say About this line, I would call it as YY line. Let's say this is some line YY and this is some line XX. So I would say about the line YY, a development of moment is there, and it's in this way. It's in this way. That's anti-clockwise. I would say below that on the bottom in this fashion. So there's a development of moment that is P into E about this line. So that's your neutral axis, I would say. That YY is your neutral axis. So that means development of stresses would be there. That means if this is neutral axis, here the stress would be 0. And from the side we have tensile stress, and from the bottom side, from this side we have compressive, and from this side we have tensile. So there is minus plus. So I would say this is P E by, so my by I. Similarly my by I. So we got those stresses. Now we need that you take any point A, sigma should be less than or equal to A. If I take any point A, I would say there is some, because of their direct stress, there is some axial stress that is compressive. There is some compressive stress. Let's take that direct value, that I would say sigma because of axial, that would be P by A cross section, that's minus times P by A. So I write minus times P by A and plus. If I take that positive value, tensile, I don't want tensile stress anywhere. So for this part, it is safe already, because you're having minus P by A and minus times PE by y by I. This entire is also negative, so overall value is already negative, less than 0. So this is already safe, this point. So this side of the section is already safe. So I would say, what is your section? So that means this part is already safe for this given loading, if the E was from this side. So this part is already safe. So we are worried about these points. And major critical point is the extreme point where your Y max is there and it is tensile. So I have to worry about this point. That's positive here. So if I write that positive value here, so that would give me some equation. Positive PE Y max by I. I about which axis? I about YY axis. Because your moment is about the YY axis. So that should be equals to or lesser than 0. So if I use those values of minus P by pi d square by 4 plus P into E, Y maximum we can have D by 2. D by 2 would be my Y maximum. And I would be equals to pi d power 4 by 64. That should be less than or equal to 0. So that means you are left with that. So your P goes, pi d square goes, and so you are left with minus 4 by d square, minus 4 plus E, and you are left with divided by D, and you are left with 32. Yeah, 32 should be at the top. That should be less than or equal to 0. So if I write that 32 E by D, that should be less than or equal to plus 4, and E should be less than or equal to diameter by 8. So eccentricity of that load should be less than or equal to diameter by 8. So if there is diameter of D, so 1, 2, 3, 4, 5, 6, 7, 8. So the load should be such that it is at a distance of, let's say the center is at 1, 2, 3, 4. So this is your center. This is your center. Let's call it as O, center. So from the center you have to go maximum, you can go to up to value of D by 8. And from this other side also you can go to maximum value of D by 8, because for our case we took that E should be from this side. It can be on this side also, it can be from this side also, it can be from this side also. So there will be development of that circle. We call it as a core, or we also call it as kern, where sigma tensile net is equals to 0. So if I join those points, there is development of that circle, what we call as core. So if the E is less or equal to that D by 2, that means your diameter of the core, if I calculate diameter of the core, that would be equals to, that should be less than or equal to D by 4. So load should be between, if the load is somewhere here, somewhere here, somewhere here, somewhere here, somewhere here, here, anywhere but within the core, that means net tensile stresses would not be there anywhere on the entire circular cross section of dimensions of dimension d. So if your net circular cross section looks like in this fashion, if your net circular cross section was in this fashion, so this was your net circular cross section of diameter, what we call as diameter was net value of, this was your diameter of d. But if the E value lies in this part, I would say no tensile stresses would be anywhere on the cross section. That means sigma net would be less than or equal to 0. That is, net compressive stresses would be all there at each and every point on this cross section. Similarly, if you take that that we call as hollow section, if you take that circular hollow section, so if you take that circular hollow section, so this one is your circular hollow section, I would say circular hollow section. Now for this case also we need to get the value of that core or cone, diameter of that cone, hollow section. Now there is some, I would say there is some center line and you are applying load somewhere. You can also solve for this line also, but for our reference we talk about this one. So let's say this is your XX line, this is your YY line, and you're applying a load of P at some eccentricity of E such that moment is developed would be some sort of in this fashion. So P into E, and there is some direct axial stress of sigma axial is equals to P by area cross section. So your area is only this one, cross section is only this part. So I would say neutral axis has formed as YY. So there would be some stress developed, tensile from this side, compressive from this side. Yeah, direction of that arrow is not, I always get stuck with this. Direction of arrow is not in this way. If I show again that because of this effect would be in this way, from the bottom it is rotating from the bottom in this fashion. So in this fashion, yeah. Yeah. So positive tensile stress gets developed on this side. So that's a tensile stress of PE d by 2 maximum. We are talking about maximum. So we can write, we have some diameter, outer diameter d outer, and we have some inner diameter d inner. So if you're talking about d outer, I would write d outer by 2 divided by I value of that section. Similarly, from this side we had compressive. Whenever there is confusion, that let's say this is some neutral axis and load is somewhere here, that's here, load is somewhere here at some eccentricity E, I would say because of this one, about this there is development of moment. So finally your tensile stresses would be at the top, bottom compressive. So you got this PE d by 2 into I, and because of direct stresses we have minus times PA by cross section. So I want that sigma net anywhere should be less than or equal to 0. That means no tensile stresses would be there. No sigma net, tensile net. So I would say minus P by A cross section plus PE d outer by 2. And what is the value of I? Can you calculate the value of I? The value of I would be pi by 64 d outer power 4 minus d inner power 4. That should be less than or equal to 0. And similarly, what is the area of that cross section? That is pi by 4 d outer square minus d inner square. So finally, if you solve it, you are left with that. You are left with what we call as yeah. If you subtract it, if you divide this part from this one, you would get a value of d outer square plus d inner square. And I would say that final value you would get a value of that 4 minus 4 plus 32 d outer into eccentricity of E divided by that we have d outer square plus d inner square. That should be less than or equal to 0. So I would say your eccentricity should be less than or equal to d outer square plus d inner square divided by a times d outer. Now, if I talk about diameter of that core, that is 2e. So that should be less than or equal to d square plus d inner square by 4d outer. So if you have that section, now, that means your then it depends on the value of d outer and d inner. Accordingly, you can get the equation. So let's have that general view of that. I would say there is some eccentricity of E here, and there's some eccentricity of E also from this side, so that is your diameter, and from this side also, and if I join that, I would get some circle. So I got some circle such that if the load is in this part, so if the load P is in this part of E, if the E is मतलब कि E इसमें आ रहा है तो such that your net tensile stresses is less than, that means net stresses would be less than 0. That is compressive. Overall stresses is compressive at any point. Infinite number of points we have on the cross section. That means at each and every point we have compressive stress of sigma. No tensile stresses is there. And let's take the final problem of this columns. Final problem of these columns. Let's have that. So you got that. You had that section. Let's say you had that section. Let's say this is your section. And we call that, this one is your line along the diagonal. I am saying that, what is the problem saying? There's some point A, there's some point B, there's some point C, there's some point D. So what is the problem saying? And the problem saying that your load is in the first quadrant. That means if you have those reference lines, let's have those reference lines. I would say there are 2 reference lines. So load is in the first quadrant such that its coordinates are passing through the diagonal. So this is your load P. I would say this is your Y and this is your X. So I would say this length is equals to along the Y. So this part is parallel to X. So I would write it as X. So X is at X comma Y. So your point load P is at X comma Y along the diagonal, I would say. So for this condition, if the load has to be along the diagonal, that means it should satisfy that X comma Y should satisfy the equation that B comma D, the relation we have with the BD, with the relation we have with the width and depth. So BD, let's write in terms of small so that confusion gets clear. So let's write that this is your small b, this is your small d, small b and small d. I would say that let's take the value of x equals to b by 4, and let's write the value of that y equals to d by 4. So your point A, point B is somewhere here at d by 4 from the x-axis, and your point B is at a distance of x equals to b by 4 from the y-axis. So let's have that point. So for this point, you need to say if the load is at this point now, at this point the load is there, you need to say what is the stresses developed on those different corners. So you need to calculate stresses at A, stresses at B, C, and stresses at D. That is net final values. So if there was only direct axial stress, on the centroid of that cross section, that means stresses at A would have been stresses at B, stresses at C, stresses at D. That is minus times P by area cross section. So that was first part. And second one is that effect of those moments, effect of those moments. So if I have this reference line and load is somewhere here at some eccentricity, what we call as x. So there is development of moment p into x. That means your reference line is neutral axis would be yy, and that bending stresses would be get developed as that of a tensile stresses on these sides a comma c, and compressive stresses on b comma d, compressive stresses on b comma d. And similarly, if you have that second effect of that moment about the x-axis line, this is your x-axis line, and there's some eccentricity of that load y, that eccentricity of that load p, that's your y, and because of that there is development of moment in this fashion, p into y. And because of that we have bending axis as x-axis, so your neutral axis is that of a x-axis. So I would have some stresses in this fashion, that stresses at the c comma d is tensile, stresses at c comma d is tensile, and stresses at the a comma b is compressive. Finally, I got the stresses that if I write the equation that stresses, let's try the stresses at a, I would write that is minus times p by bd, plus because of this one we have a positive. What is the value of this one? Can you get this value? What is this value? What is the maximum value we can have? That is p into x, and value of x is also we know p into x into what is the value of x maximum we can have? Maximum value of x we can have, that's x maximum. So that's equals to b by 2. So b by 2 divided by what is the value of I about the axis, that is about the y axis. So I will write Iyy, that equals to dbq by 12. So we got a value of p into, and you substitute the value of x also equals to b by 4. So you got a value of b by 4 into 6 times db square. So final value of 6p, that is 3 by 2. Final value of 3 by 2 p times b, so db 3 by 2 of p by bd, 3 by 2 of p by bd, that's positive. Final value of 3 by 2 of p by bd. And third one, you can also calculate that the stress developed here is equals to some moment of p into y, this moment of p into y. And what is the value of y maximum we can have? Y maximum we can have about the axis, that is neutral axis, about the x-axis, that's your neutral axis for this moment. So y maximum we can have equals to d by 2. And if you substitute the value of y also equals to d by 4, and you divide by that what we call as what is the INA about this x-axis, that is bdq by 12. So this value is also equals to 3 by 2 of p by bd. But if you are talking about point A, that is compressive. Minus times 3 by 2 of p by bd. So net value of minus times p by bd, you got stresses at A. Now you want to calculate stresses at point B. Initially the p by bd is same for the entire corners for A, B, C, D. Now what is the stress at B because of this moment? Stresses at B, we have this tensile, we have this compressive b 3 by 2 of p by bd. So minus times 3 by 2 of p by bd. And for the third case, stresses at B we have also tensile, that is compressive, we have also compressive, that is minus times 3 by 2 of p by bd. So 3 by 2, that is 2 times, and we have one more, that is 3 times net value of 3. Is it net value of 3? Is it 4 times actually? This is net value of 3 by 2 into 2. So net value of 3. So final value of minus times 4p by bd. Do you got this one? Yeah. Minus times of 4p by bd. And what you need to calculate stress at C. Initially it would be minus p by bd. And this would be also 3 by 2 of p by bd. This would be also 3 by 2 of p by bd. Similarly for the sigma d also we have minus p by bd, and 3 by 2 of p by bd, and this one is also 3 by 2 of p by bd. Now we want to see what is the sign sigma c. So for first one is that positive. For the c we have first one is that positive, and second one is that second one is also positive. So for the c we have both positive. So finally we got that 2 minus 1 net value of positive p by bd. And if you are talking about that d, for the point d you have tensile, you have compressive minus, and in this part you have positive tensile. So minus plus, I would write minus plus. So this gets cancelled, so you are left with value of minus times p by bd. Now we want to calculate, we want to draw some conclusions here. So I would say your maximum stress we can have, that is 4 times p by bd, that is compressive. So that's maximum compressive stresses, or maximum stress we can have, that is 4 p by bd, that is for at point b, that is compressive. And I want to say what is the stress at a, that is p by bd, and if I see stress at d is also same, so stress at a is stress at d, that is same, that value of minus p by bd compressive. And there is only one point where net value of tensile stress has developed, that is sigma c, that is positive. If I say what is the maximum tensile stress we can have, so I would say maximum tensile stress we can have, that's at point c, that is equals to p by bd. So the conclusion is that if your point is away from that eccentricity, your point c is away from that load, and there is development of tensile stresses on this point. So there is a possibility if your point A is away from that eccentricity, there is a possibility that on this point there is development of that tensile stresses. Based on this factor that if you have this neutral axis, I want to say what is the stress at here. You are applying load of P here. That means at some eccentricity, I would say on these fibers we have tensile stresses, and bottom we have compressive. So this was the end of that, what we call as columns. Hope you enjoyed the series of that columns. Thank you for watching this series of what we call as concrete path, strength of materials, the path that delivers those shear forces, bending moments, torsion of those shafts, shear stresses, Mohr cycle, etc.